Okay, so thank you all for joining today and the next 2 days, for those who didn't make it all 3 days, for our yearly team meeting. We took a little longer than last time. As you can see, the last meeting was in February 2023. But since then, a few things have changed. But the team members remain more or less the same. This is a photo from last year's team meeting. Let me see if I can minimize this over here. I think most of us are in there, but we'll see some more people this year, thankfully. Let me try to get my screen working here. Okay, so I just thought, a normal thing, I give my overview here about different things. I'm not going to go through everyone here, but I thought I'd mention a few people who are retiring but sticking around in some different ways. I think you all know Andy Ackerman, our cloud expert, has retired. My sad face, but he's still helping out, smiley face. So he'll be around. He's married to one of our members who is not retired, so he has no choice. Of course, Igor's here. People in boldface are giving talks. Rory is here. Mark is here, and Mark is also retiring, sort of. Congratulations or condolences, yeah. Andrea is going to give us a talk. One of our newer team members. Kulshel, he's online up at MIT. We had some issues getting him in the building, of course. Connie, our MVP, is here. Scott, I hope, is online. He couldn't make it up. Nancy is here, of course. Tony Leboissetier.
Recording in progress.
Oh. Please mute if you don't mind. Echo there. Rakesh Mogul, he'll show up tomorrow. It's a little early for him. He's out in California on our Pioneer Venus mass spec stuff we've been working on. Jan, of course, on his dust model is going to talk. Linda, Paleo Earth and her cuisines stuff. Linda, you're here, right? Let's see. Oh, she's in the back there. Yes. Kostas, he's giving the second talk on Planet 2.0 and giving another talk on science. I remain a slave, as I said. And then Eric does our rate of transfer, as we all know, but Eric's also mostly going to give a science talk later in the conference. Okay, I thought I'd just go through a few things. Some of this, many of you know, some of you don't. Very recently, we found a fix that was known from 2015 in the cloud convection scheme, or the convection scheme, was causing a lot of problems with runs that are a bit warmer. For those of you that have been using the model for many years, as you know, when we started modeling warmer climates, we were getting these nans in the radiation, never could figure out why. We thought for years it was radiation, although the radiation people said it was not the radiation. The radiation people were right. It was in the convection. And it was a fix from 2015, thanks to Igor, basically, who dug into this and then talked to Max. And you know how good Max's memory is. Max said, oh, yeah, I put that fix back in 2015. Why don't you guys have that fix? Anyway, now we have it. It's working. I'm very happy about that. Last year, Tom fixed this problem with the equation of time and the calendar, but that's been working really well. Nancy's led this amazing effort to overhaul the dynamic lake scheme and the runoff. Thank you for all that heavy duty lifting, Nancy, and maybe we'll hear a little bit about that later on. The KPP chemistry was making great progress. Maybe Kostas will talk about that. He got the Earth people involved. They were contributing huge amounts, and then a lot of those people are leaving us, apparently. So I'm not sure what's going on. He'll give us some updates. And Kostas will also tell us about the new release of the model, which we released a few months ago, which I'm really glad we did because the program managers have been breathing down my neck about this since we've been promising it for about 2 years. So, but now we have this. I think recently we had a referee report. Someone was saying, oh, but this model hasn't gone through peer review. And I thought, have any GCMs been gone through peer review in this planetary science business? I think ours is the only one that ever even wrote a paper about the model. I'm a bit appalled by that. But Kostas is going to update us on that. For the next release of the model, Andrea has been doing a lot of really great work with Max on hooking up our radiative transfer scheme in E3, variable mean molecular weight of the atmosphere, which we've talked about doing for years, multiple condensable species, and CO2 clouds we're very excited about for ancient Mars stuff. And I think one of the other things to get working eventually, once we're a little farther along, is get Tom to get the calendar hooked up, and we'll have to work a bit with Max and Andrea for that. So thank you, Andrea, for all that heavy lifting you've been doing, and work with Max, which can be challenging. ocean biogeochemistry. So we're going to see a really nice talk by Paul Lerner on day 3 about that. So Paul and Natasha finally got that working in ROCKE-3D with a low-res version of the model. And that paper, we have a paper under review. Basically, we got the referee reports back. They're pretty straightforward. Paul just needs to turn the key and it'll be accepted, I think. And then Jan's going to talk to us about the dust stuff he's been working on. We had some problems. We found a nice bug, I think it is, right? That the dust emission needs to scale with snow fraction.
That is not really the bug.
That's not really the bug. Okay, anyway. Well, other bugs. Anyway, he's going to talk about some of that in his talk on day 3. I think you all know about this, but I always like to bring it up every year. We're doing, our different variations of community service. Every year we're doing our ROCKE-3D tutorial. And I think it was, again, pretty successful this past May. We had about 20, 25 people online, I think, for that. We didn't have anybody in person this year, just those of us running the tutorial. And as usual, all those tutorials are up online. For myself, I have been doing my version of community service. This year, I had 5 bachelor's thesis students from Uppsala. As I say all the time, I think one of the really great things we did with this model from the very beginning is putting all the summary data for every paper online. It makes it really easy for me to do thesis projects because I can just say, here are 10 different papers we've written over the last few years. Here's some ideas for things you can do. All the data sitting over there, go for it. And this has worked brilliantly year after year after year. These kids can download the data, analyze the data, and do what they want with it. So this is a project that was looking at habitability of TRAPPIST-1D. I finally submitted that paper, the paper that involves the simulations themselves, just a few weeks ago to AppJ Letters. We'll see if it gets rejected. This is another thesis, simulating spectra for potential exovenus-type planets by Erik Johansson. A third one, looking at TRAPPIST-1E simulations, very similar, using planetary. All 3 of these papers are using planetary spectrum generator. And they figured it out more or less on their own. They read through all the tutorials, the online handbook. We had one telecon with Vincent Kaufman, who's going to give a talk later on in the meeting. And that was extremely useful. So Vincent was really helpful getting that working. And then I had a really fun project with 2 engineering physics students named Norea and Tira, looking at habitable worlds and multistellar systems, searching for Xandar in a triple star system. I had them give a talk to us a few months ago. Some of you participated. Rory helped a bit with the dynamic simulations. That was really the most fun project. I got this idea when I was with my son at Disney World in the Xandar roller coaster ride. We were in a really long line and they had all these videos about the Xandar system. And I thought, hey, man, we should do this system. And these young ladies agreed it'd be fun to do. And again, Rory was very helpful getting that to work.
So that was a business trip.
It was a business trip. Only I could get NASA to pay for those Disney World tickets, man. Just insanely expensive. And then, of course, this summer, we had 2 summer interns, again using planetary spectrum generator, Jason Fitzgerald, looking at our old Proxima Centauri B simulations that Tony led, that was published back in 2018, and then Mackenzie Smits looking at TRAPPIST simulations and looking at habitability. And I want to say thanks especially to Donnie, Andrea, and Tony for helping out with them, since I was on vacation for a few weeks there and wasn't able to help advise so much, but that was really amazing. I don't know if this is community service, but I showed up on an episode of The Unexplained with William Shatner. Unfortunately, I didn't interact with William at that time, but I was dragged over to Brooklyn. I was telling Rory and Kevin at breakfast this morning, and I sat there for 3 hours answering questions and doing all this stuff. And in this episode, I show up for about 15 seconds explaining how Venus spins retrograde. I'm hoping that they take some more of my comments in future episodes, but we'll see. These are just some papers I've been working on with different people that I thought I would just mention, Rakesh is going to talk about this work on day 3, the Pioneer Venus stuff at the top. I just mentioned Paul's paper on ocean productivity related to the obliquity of the planet Earth. My TRAPPIST-1D paper was submitted. Eric and I are working on this Archean paper that I think we're getting pretty close. And I had a really nice meeting, like a serendipitous meeting with John Marshall about some work he did a few years ago on the dynamics of oceans, which are playing a really big role in the Archean, at least in our set of simulations, about whether you get a full snowball world or not, or water belt world, kind of things like that, which is really interesting. Marshall and Tony have been working on deep ocean modeling, and we're going to hear from both of them about how that's going, and especially on looking at Enceladus. Andrea's going to talk about her work. I think, are you going to talk about this periodic oscillating stuff, or are you going to talk about a different one?
Yeah, I'm going to talk about it.
Okay, good.
Part of it.
She's going to get into that. It's going to be really good. Donnie's going to talk about his land planet stuff. We're going to have someone from University of Bangor and Wales, not Maine, Sophie, who works with Matthias Green. Matthias Green is one of the top oceanographers in the world, who I met through Rory many years ago, and we continue to do some projects together. This is, again, looking at some deep time future Earth scenarios that I did a few years ago with Matthias and Rory and a few other people. And then Jen Carter, who's a former PhD student of Kevin's. We've been working on for a few years on this paper that looks at the hyperillumination of exoplanets, and she's going to talk about that. I think that's really interesting. We've talked about actually putting some of this into the model itself for really close-in planets that are over-illuminated, basically. More than 50% of the planets illuminated by the star. And then my former master's student, Viktor Sparrman, who is now a PhD student at the University of Copenhagen with Anders Johansson's Planet Formation Group, is going to talk about a paper that we wrote, we worked on for a few years from his master's thesis. It was published in APJ just a few months ago on habitable phases of outer extrasolar worlds, meaning when our sun goes red giant and even into the AGB phase, how that changes the habitable zone for our solar system and for similar type stars. So I think that'll be kind of a fun talk. Yes.
We got that published.
Yes.
That's accepted.
Yes. Also, the paper that Kevin just pointed out that we got published in Maxent with Vasuda and Kevin, they're going to talk about that in his talk a little bit later today. Thank you, Kevin, for reminding me of that. And probably there's something else. Oh yeah, also the paper with Jan, which is working on also on the dust, on the Mars dust stuff. And these are some other works in progress. I'm not going to go through all these, but just different things we've been working on the last few years. And I also got dragged along with Donnie into doing another ISSI review project. This is an exoplanet book, and I think I'm on 4 of the papers in that book. These will all published in Space Science Reviews, just like it was with the Venus book I worked on a couple of years ago. And you can see titles there with different people leading different chapters. For those of you that know anything about TRAPPIST and observations, Elsa Duquois is working on TRAPPIST-1 observations with JWST. And for those of you that are geophysics people, you'll know Paul Byrne, who's he's actually head of AGU planetary science these days. I don't know how he has time to do that. He probably doesn't sleep much. At least he doesn't look like he sleeps much when it's due. Future, yes. So as all of you know in the room, we got this 5-year ICAR funding starting about a year ago from today. That's why I thought it would be a good time to have the meeting about a year from now. Our strangely worded previous funding model, independent scientist funding model, NASA, come up with really strange names for things, expired last year. We only got one of our proposals accepted to seek this year. I thought was kind of disappointing. I also got some money for some disk space sort of end of the year funding thing that they offered, and I've applied for that several times, and I finally got 50,000 to add some disk space to server in the building. But I think normal thing, we need to write more proposals. I say this every year. We need to write more papers. It's the currency of the realm. So let's work on that. Okay, so I thought with the time remaining that we could go around the room and tell who we are like in a couple sentences? Does that sound like a good idea? Let me stop sharing my screen here. And yes, so why don't we go to my right? And Kevin, can you tell us who you are? Well, we know your name's Kevin.
And right, let me. I don't know if I can do this without.
You're on mute. Yeah, you're on mute. Okay, good.
So
Yeah,
that,
you're
that,
fine. That
yeah,
works.
that can
That
be-
works. Yeah,
Great,
you're
great. I'm Kevin Knuth. I'm a physics professor from the University of Albany. And we are working on the machine learning systems to predict atmospheric spectra based on the planetary parameters.
Chris Close, contractor here at GIS, and been here for a few years with the team and going to be talking tomorrow about slowly rotating Earths and habitability.
Kostas Tsigaridis at Columbia University here at GIS. And then I'm doing all sorts of stuff related with atmospheric composition, aerosols, gas phase chemistry, and I will be leading the Planet 2.0 paper. And yeah, we'll have some recently funded work that the funding is not even ready yet. I'll talk about that on Wednesday. And today I will be talking about Planet.
I'm Mark Chandler. As you heard at the beginning, I'm retiring at the end of the year, but I'm retiring from Columbia, 37 years at Columbia University. I'm still going to be working with the American Museum of Natural History, so I'll still maintain a connection with GIS through that. But that work, I work with in the education department there, the science education. I'm a paleoclimatologist by background, and I have a couple of projects related to paleoclimate and that overlap with exoplanets. And we'll see if they actually happen ever or not. You kind of don't know at this point in time what's going to happen in post-retirement, how much energy you'll have to work on your science still. We'll see. Maybe my wife will tell me.
So we are Linda.
Oh, yeah. So I'm Linda Soul. I'm actually in transition from Columbia to the contractor. And as Mike mentioned, I do paleo Earth.
Andrea.
Andrea Clarkson. I am a contractor, postdoc, here for 2 years now. I came from background in astrophysics, now planetary. I have several different projects pipeline that I will be doing over on Wednesday.
Nancy.
Hi, I'm Nancy Kyung. I specialize in land ecosystem and atmosphere interactions. And because land ecosystems depend on water, on ground, I also do a bit with surface hydrology development and environment.
I'm Rory Barnes. I'm a professor of astronomy, astrobiology, and data science at the University of Washington. I try to study everything to do with terrestrial planet evolution. Kind of originally started out thinking a lot about orbital dynamics and tidal effects and how those affect habitable planets, but now I work on atmospheric state, geochemistry, all sorts of things like that. So I try and kind of give boundary conditions to a lot of the modeling efforts that all of you work on.
I'm Donnie Glazer. I'm a MPP postdoc here at GIS. I'm probably interested in arid environments, arid planets, and so yeah, land planets and habitability of land. Yeah.
Hey, I'm Tony Aguestier. I'm a part of the development team here at GIS. I spend a lot of time working on the sea ice on the Earth side of thing, and when I'm getting too depressed looking at the sea ice continually melting on Earth, I escape with a ROCKE-3D. I work mostly on the ocean, and tomorrow I'll show you some exciting new updates on our ocean and sea ice in ROCKE-3D, and also an update on our Icy Moons project.
I'm Roman Rafikov. I'm not part of the collaboration. I'm kind of external person, a professor at the University of Cambridge, just visiting here and was invited to give an overview talk. Generally, I work on dynamics, celestial mechanics, n-body dynamics, fluid dynamics, and so on. So would be interesting to participate in this meeting and see what you guys are doing.
Igor.
I'm Igor Olin of Columbia University again, and and I was here like for more than 20 years working on various parts of climate model developed here. First, Earth model, now on this planetary model. Yeah, I guess I'm involved in most part of the model, but mostly it's land surface. In particular, I developed snow models. On this meeting, I will be presenting exotic ICES model and the snow model, which can handle more than one condensable. I guess you will hear about it. Yeah.
Okay, thank you. Jan?
I'm Jan Korwitz. I work on the basis of my own company, and I'm also have been affiliated with GIS for quite a while. And I started out working on everything dust related for Earth about 26 years ago, and about a few years ago, I started to work on dust also with respect to Mars.
Great. Okay, how about online? I guess I can call, oh, Zoe, yeah, sure.
That's fine.
Nope.
Zoe, I'm the librarian here.
Yep.
Since Mike graciously invited anyone that gets to attend, I'm just sitting in on a few sessions because I feel so freaking awful.
Thank you, Zoe. Yeah, I wasn't sure you wanted to introduce yourself, so thank you for doing that. Okay, so we go online. I guess I'll just call out people as I see them. So in order, how about you, Victor? Can you tell us about you?
Yeah, hi. I was one of these bachelor's thesis that used some ROCKE-3D results that you spoke about earlier. So I did my bachelor's thesis with Mike over in Uppsala, but I'm now doing my PhD in Copenhagen.
Great, thank you. Sunny.
Hi, everybody. It's good to see everyone. Sonny Harmon. I was a postdoc at GIS briefly and have been working with Kostas for a number of years now. He's going to be leading the talk we have about some recently funded work that we're going to be starting hopefully in the new fiscal year. And I'm going to be talking about some work I did with an intern we had at Ames over the last, not this summer, but the last summer. But I do atmospheric photochemistry and think about atmospheric lifetimes and against escape.
Eric.
Thanks, Mike. Hi, everybody. I'm Eric Wolf. So I've worked with the ROCKE-3D team since I think it was summer 2017, picking up from David Odmundson, who his exit from the community was definitely a great loss. He was very knowledgeable. So I help with Socrates over the years. Some of you also may know me from the from my NCAR CSM exocam modeling work as well. So yeah, I'm Eric. I think most of you know me, but for those who don't, nice to meet you.
Thank you, Eric. Thomas?
Hi, everyone. I'm Thomas Fauché. I'm a scientist contractor at GSFC. I'm the co-lead of Cuisine, which is this intercomparison project. Many of people at at GIS and ROCKE-3D team are part of. So yeah, I'm a ROCKE-3D user among different GCMs. And I'm also the co-developer of the planetary spectrum generator, specifically the globes module, which is really a way to directly ingest GCM output and predict spectra. And I'm going to talk about that tomorrow with Vincent Kaufman.
Thank you, Thomas. Kaushal.
Hi. Hi, my name is Kaushal. I'm a postdoc based out of MIT with John Marshall, and I've been working with Mike and Tony on the Icy Moons project. That's what I'll be talking about tomorrow. Nice to meet you all.
Arnaud.
Hi, everyone. Thank you all for having me. It's great to be here online. So I'm Arnaud Salvador, postdoc at the University of Arizona, working with Ty Robinson. Tomorrow, I'm going to talk about the early evolution of Venus, because I've been working on the early evolution of magma ocean in interaction with the atmosphere. And also, I work on characterization of Earth analog exoplanets.
Connor.
I'm Juan O'Connor, now a graduate student at University of Michigan, working on climate modeling and observational modeling. And later today, I'm going to talk about some work I did with Nancy and others when I was a student of hers. Glad to be here. Thanks.
Great, great. Scott.
Hey everyone, I'm Scott Gazage. I'm at NASA Goddard in the Planetary Environments Lab. I've been on the ROCKE-3D team in one form or another for a while now. I don't know, 8, 9 years, however long we've been doing this. I mostly do Mars atmosphere studies day to day, and I've done some of that with the ROCKE-3D team, working with Jan on the current Mars project, and I've done paleo Mars modeling with ROCKE-3D in the past. Right now, I'm doing some of the Phanerozoic Earth climate modeling as part of the ICAR project, but that's in way too early of a state to talk about it, so no talk for me this week.
Okay, thanks, Scott. Mariela.
Hi, everyone. Well, my name is Mariela. I'm a researcher in Buenos Aires, Argentina. I spent 6 months at this at the beginning of this year, and I'm starting with ROCKE-3D. So, well, thank you.
Thank you, Mariela. Avi, are you there? We don't see you.
Yes, I am here now. You can hear me?
Yes.
Yes. Yes. Mandell, NASA Goddard. I'm not officially part of the ROCKE-3D team, but have, of course, been involved through most of our work with the Sellers Exoplanet Environments collaboration, which ROCKE-3D has been part of for a long time. But I mostly work on mission concepts for exoplanet characterization and observation and motivation for those missions. So I'll be talking today about mission concept, which could give us spectacular 3D maps that ROCKE-3D models could be applied to. So looking forward to talking more about it.
Oh, somebody's phone's ringing. Thank you, Avi. I think all we have left is Hector. Hector, we can't see you.
Hello, hi, my name is Hector. I am a PhD student at the University of Washington. I work with Rory Barnes, and I am slowly, I'm slowly getting integrated with the ROCKE-3D. I'm interested in being part of it, and I work with vPlanet, and what I do is exoplanetary simulations. Currently I'm looking at energy balance models on how orbital, atmospheric, and stellar parameters affect the climate of exoplanets. One project that I've been working lately that I presented at the ROCKE-3D Journal Club recently is the climates of Gliese 514b, which is a highly eccentric exoplanet, and we want to know if there's any point, if there are any permutations of or combinations of parameters that can give temperate climate for habitability.
Okay, great. Thank you, Hector. Thank you all. That was really nice. And somehow we stayed on time, more or less. So, Kostas, I think you're up. Do you want to share your slides? Sure.
Okay, perfect. So, things. Okay. So I'll be talking to you about the ROCKE-3D version 2, which is internally we call it Planet 2.0. And I have shown you a few of those things that I will be showing last time. And but I think that it is important to highlight what is the key message I want to pass with why we're supporting several configurations of this model, and also how it is different when it is different compared to the previous one. And for the second maybe half of the discussion, I will be showing you a real life example on how you can take what is provided to you and then use it for creating your own world or your own flavor of ROCKE-3D, and what you need to be paying attention. So ROCKE-3D is publicly available. You can see the website up there under the title. And when you go there, it lands you to the text on the left. And if you click on the download the latest ROCKE-3D source code, you go to the page on the right, and you can find there both Planet 1 and Planet 2 versions. I see no reason why you will be using Planet 1 if you are starting now, but there might be a reason for you to use Planet 1 if you have been working with it for a number of years, but transition to Planet 2.0 should eventually happen, I guess. And as Mike highlighted, we have the ROCKE-3D tutorials that are available online also on that page, and you can download both the slides and also the videos, and the slides for just 2 years and the videos for all. And we're always available to answer questions within reason, obviously. So what's in ROCKE-3D version 2? It is obviously all of version 1. And then we have on top of that, the most recent version that the model has used for the CMIP6 project that was something like a few years ago. And we also have on top of that, some structural changes and related with atmospheric composition and some atmospheric composition updates. So the structural changes, if you are looking deep into the code, you will see that more physics are column physics compared to having 3 dimensions. And that is even more happening in E3. And then, but mostly it is, there are no real changes in terms of results there. And then some atmospheric composition updates that are quite major compared to the CX6 version of the model. But ROCKE-3D does not officially at least support any prognostic atmospheric composition. So we don't have to worry about those. I will only be discussing about the standard way that most people are running ROCKE-3D, which is with fixed atmospheric composition of the main gases and greenhouse gases. Then there are some additional non-Earth updates, and but these are also part of the model release. And in any case, internally you can find, I have some names here listed for branches and things that for the people that are actually having access to our repository. But the key point is that we have a development branch of Planet 2 that will keep evolving and eventually will become Planet 3. And we have a Planet 2.0 tag, which is the released version of the code. Everything other than ROCKE-3D on this slide has in practice the same climatology if you run it for long enough to get the climatology. So there will be some numerical differences here and there, but the climatology is the same. And this is equivalent with the CMIP6 Earth climatology that the model is having outside ROCKE-3D, the model E, which is the host, the parent model. So the new things in ROCKE-3D, there are a lot of physics and parameterizations updates. We'll go through some of them into the ROCKE-3D paper. And we'll go through many of them into the Model E CMIP6 version of the paper of the model. So you have to really look into those. The important thing is that we support 2 radiation schemes, GIS and Socrates, 3 different atmospheres, 3 different oceans, and 2 different resolutions. We have geothermal heat flux, and I added a nice plot over there in the 2 different resolutions. Support for thinner atmospheres. I expect that at some point Igor will say something about that in these 3 days. Improved present-day Mars, and I guess that Jan will touch on that. And support for deeper oceans that I guess that Tony will be touching. And as far as I know, this is not final, it's ongoing, right? So in terms of configurations, I have this very weird acronym at the top right that I'm going to demystify right now for you. So P2 stands for Planet version 2. So it is one of the template runbacks, and by that it means the supporting ROCKE-3D configurations we are using. So everything that starts with P2 in the model code, you probably care about it. Then, with this bright yellow that is not so clear, you see there is the G and the S, which stands for the GIS radiation or the Socrates radiation. And then for the atmosphere, we can have either the pre-industrial Earth, exactly as described by Model E for CMIP6, either atmosphere that we call X, which is equivalent with the ROCKE-3D version 1, and that is without aerosols, without ozone, without stratospheric water formation from methane, but it has molecular oxygen. And then we changed that into our favorite ROCKE-3D configuration, which is called N for anoxic. And this is essentially the same as X, but with no molecular oxygen and also argon. So everything, the carrier gas is 100% nitrogen plus some greenhouse gases, you know, some methane and some CO2. So then the ocean, we have three different flavors of it. One is no ocean, which is essentially you prescribe sea surface temperature and sea ice extent and thickness. And the other one is the Q-flux ocean that has 100 meter mixed layer depth and zero heat transport. And I emphasize that because in a non-supported version of the ROCKE-3D version 1, the Q-flux ocean was that of having heat fluxes as of present-day Earth. Now we have zero heat transport, which is the standard in the community. And I will show you some results about that. And then the dynamic ocean is also is probably the workhorse that the people will be using here. And we have two different resolutions, F for fine, M for medium. And you can see the numbers there. Essentially, this 2 by 2.5 in the atmosphere and double that in the ocean for the F, and 4 by 5, both in the atmosphere and the ocean for the M resolution. Another difference from ROCKE-3D for version 1 is that the M resolution, the medium resolution that we are using, is now having 40 layers by default compared to 13 I believe 13 or 20 layers. I don't remember exactly. I think 20. Yeah, the 20 layers that was the standard for Planet 1.
It was 20 if you used the GIST scheme and 40 if you used the Socrates scheme.
Okay, thank you. I was not aware of that. Actually, I'm certain I've seen that someplace, but I don't remember that.
Yeah.
Okay.
Can I just have a quick question?
Yeah.
With regards to the ocean, when you use a shallower versus a deeper ocean, are you actually, squishing more layers into a shallower ocean, or are you like lopping off layers? Like when we use 1,000-meter ocean instead of a 6,000-meter ocean.
So it depends on the configuration. So if you are thinking of the 13 layers ocean compared to the 40 layers ocean, I think that they both go down to the bottom for Earth configurations, but then for non-Earth configurations, you decide on that.
And you can obviously design your own vertical resolution and grid. Like it's you don't have to stick to this. Certainly, if you want to add some layers, it's up to you to decide, your optimal resolution for.
But typically, Mark, we did lop it off. So typically, if we did 1,000-meter ocean, we would pick a level in the 13-layer ocean that was close to that and use that basically.
Right. So that helped it and run faster, right?
Yes.
Yes.
Absolutely. Come to equilibrium faster.
Yes.
So our favorite version is Socrates with an anoxic atmosphere, dynamic ocean, and then you pick your resolution. And usually you pick your resolution based on how big the planet is. If you have Mars, then you can get away with the coarse resolution probably. And then if you go to super Earth, for example, then you will probably need the fine resolution, but it depends on you. Model performance, I will go really quickly here with some findings. So all the columns that you see here are the different configurations that we are supporting actively. And on the y-axis, it is an approximate measure of wall time in minutes per day. So some key findings here is that the fine resolution is slower than the medium resolution. That's no surprise. That the Socrates radiation is in general slower than the GIST radiation. That is also something that we know of. If you're simulating with Socrates the ROCKE-3D version 1 atmosphere or the anoxic atmosphere, they are comparable in speed, but if you simulate present-day Earth, it is slower. And this is probably because there is a big performance penalty in Socrates for simulating aerosol and ozone effects. Then the prescribed and the Q-flux oceans are comparable in performance, but they are faster than the dynamic ocean. That is also no surprise. this shows up mostly in the fine resolution, but the ocean has many more layers and many more grid boxes. In the medium resolution does not really show up that much. And then in general, it appears that if you put all the bells and whistles in the model, like both dynamic ocean and fine resolution and everything the most complex possible, the models are kind of equally fast within the margin of error of this metric, which is not an exact metric. So it appears that the bottleneck is the resolution if you go to very high resolution, to everything included, and not Socrates. Which might mean that Socrates is a little bit more optimized when it comes to higher resolution in some difficult calculations compared to our ocean, maybe. But anyway, something to keep in mind. So the net planetary radiation is the key metric to see whether your model is in equilibrium. And again, I'm showing you here in different colors all the configurations. We have an arbitrary limit that it has to be within 0.2 watts per meter square from 0 if you want your model to be in equilibrium. And these are long climatological simulations. All the box and whiskers are from 100-year simulations for every one of them. And the key thing is that if you see an interesting thing is that if you see those three bars right here, that they have a much higher variability than nearly anything else. These are the GIS radiation with a prognostic ocean, dynamic ocean, and fine resolution. Much higher natural variability than anything else, just something to keep in mind. And also there are two simulations that are outside the 0.2 range. We couldn't make it to go down there. It's okay, it's not far out. The spin-up time is very important if you are picking up configurations, and especially when we are separating the prescribed versus the Q-flux versus the dynamic ocean. So the prescribed ocean, since it is prescribed, there is nothing to equilibrate there, and the atmosphere equilibrates very quickly. So within a decade, you are done. And you see at the top panel the radiation, the total radiation of the planet, and then at the bottom is the global mean surface air temperature. For the Q-flux ocean, it takes maybe a century to equilibrate, maybe even a little longer in this case here. And it is much slower than compared to the planet 1, which is the green. And I don't know why that is. I didn't explore it really. But this is just, again, an order of magnitude to keep in mind. If you are creating something very different from what you have, or you start from scratch in any way, you will need at least a century and you will also need to keep an eye on those diagnostic statistics. And for the dynamic ocean, that's an extra order of magnitude here. So you need at least a millennium, if not 2, depending on the configuration. For example, the red line here, to reach the modeling equilibrium. The important thing is that we are providing equilibrated restart files. So for all 36 configurations that we support, we will be giving publicly the restart files to start from there. So for the most part, you start there and at least you are in some semi-equilibrated state if you are making decent changes and you don't have to start from scratch again. That's a quick view. I can spend the whole talk here. So this is just to give you an idea. I am taking the simulation that we said that is probably the most commonly used, which is up here, Socrates, no oxygen, dynamic ocean, and medium resolution, and I plot at the very end. And then I plot in this here a number of different diagnostics as a function of how they differ climatologically from the control simulation at the very end. So if you see white, it's the same. If you see dark colors, either dark blue or dark red, then it is very negative or very positive. So there are big differences. And obviously, I'm not going to expect that you even know what these things are here. So very briefly, there are the clouds in planet 1 are going higher than in planet 2. The Q-flux ocean is having much more ice and snow This is why it is red in all those blocks here. And this is because you have a zero heat transport that from in the water, so it gets much colder. And but I only have it here. It will show up in the planet in the ROCKE-3D paper, so I don't want to spend more time on this. Here's what I just said about the ocean. You see that in for the sea surface temperature, the model is in general, all configurations are within like a couple of degrees, except in the Q flux that they are very low. It is, again, because of the heat transport. This is exaggerated in the GIS radiation and the present day atmosphere. And also the M ocean is in all cases colder than the F ocean, including P, the prescribed, which is probably an interpolation thing that happens there. I don't know. Just something to keep in mind again. If you zero out ozone, and this is a vertical plot from the surface all the way to the model top, you see that the global mean temperature as a function of altitude and also ozone. When there is ozone, temperature in the stratosphere is increases. Actually, when there is ozone, there is a stratosphere. Otherwise, there isn't one. And but the water is always staying low in the stratosphere. In the case of the cold stratosphere, this is because it cannot hold more water, probably. In the case of the warm atmosphere, stratosphere, it is because there is a cold trap right here. This inversion in temperature does not allow water to leak into the stratosphere, so the water stays in the troposphere. The GIS and the Socrates radiation are very similar in those plots here. An interesting thing to see is that this blue line, the dark blue line here, this is the planet 1.0, and it shows that it has a more gradual decrease of temperature around where the tropopause is supposed to be when there is no ozone. And that allows for more water to go into there. And that also leads us into more clouds. So if you see the total cloud fraction here in the ROCKE-3D version 1, it has some cloudiness higher up. Everything in the troposphere looks very similar. And yeah, this is just for reference, this is the liquid clouds portion, and this is the ice clouds portion. But the important thing is the total, that there is this difference here that you might want to keep in mind. Anyway, I can keep going on, but I prefer to spend the rest of the time for giving you a real life example. So we have this project that I will be discussing about on Wednesday. And we wanted to take present day Earth, but have a generalized physics. So our supported present day Earth atmosphere, which is the one here on the right, is having some Earth-based tunings that we wanted to keep there on purpose, just in case someone wants to take ROCKE-3D and simulate present day Earth as good as possible. But in our case, we want present day atmosphere. And by present day, I'm sorry, I mean pre-industrial, but for ROCKE-3D doesn't make any big difference. So we wanted that atmosphere, but we wanted the generalized physics. So we took the anoxic atmosphere that has generalized physics and the oxygenated atmosphere that does not have generalized physics, and combined the two. And we say, okay, that will be our new thing. It's not a supported configuration in ROCKE-3D. And in retrospect, it might have been a good idea to be supported. But anyway, so what we did is that we allowed clouds to go all the way to the model top, just in case. We added some extra diagnostics for lighting and flammability. That's irrelevant. We changed some boundary conditions for the input files that force aerosols and ozone, but this is only climatological. We are very equivalent. And we removed irrigation and crops. We removed the Earth-specific gravity weight drag, and instead we use a generalized approach for that. We removed some Earth-centric ocean constraints that had to do with tides and with marginal seas and some heat, some tidal dissipation, I think. Some ocean constraints anyway.
Specifics about gateways and stuff.
Yeah, things
hard-coded to the present day Earth.
Mostly they are hard-coded based on the rotation of the Earth. So it's not about the topography, because we are not touching that. It is mostly based about more about tides and large planetary scale parameterizations. We remove volcanic aerosols. I am changing my mind on that, so I'll probably put them back. And then we remove the Earth-centric clouds in homogeneity correction, which assumes that the clouds are approximately what they are right now. So we wanted something more general, and we removed that, and we removed some other diagonal. And what happened is that this is the net radiation of the planet. So you see the red one is the tail end of some simulation that we start our climatology that we provide to the community, which is the green one. And then our case went cool, went quite negative in terms of the net planetary radiation. And then it kind of recovered. And I have now like 20 more years of this simulation because it's still running. And it kind of recovers. But it took a bit. And I'm like, okay, let's think about it. Is this expected? So I say, let's take the prescribed ocean and see what happens with the present day atmosphere. And it looks good. And then let's take the prescribed ocean and combine it with generalized physics. And it runs cooler by about half a watt per meter square. And that's an important number because we essentially balance the model based using the prescribed ocean. And this was a major component in the ROCKE-3D paper. And so what's this half a watt? Is this expected? And so we go back to this paper that many of you have seen, some others will see very quickly. And there is this plot, it's figure 2 and also table 2 that explains what the simulations are. And we wanted to see when we take away the components that we took away, how does that matter? So we start from here. This is our base simulation that we started. It is not balanced in this plot, so don't worry that it is not at 0. And then if you take away, let's say, irrigation that we took away, you move to this green box, green circle, and there is hardly any difference. And if you take away the gravity wave drag, then you go down by like a half watt per meter square. And if you take away the clouds in homogeneity and use a generalized one, again, you stay approximately at the same line. So what really happens is that irrigation and clouds did not alter the radiative balance of that model, but it altered by half a meter square the gravity wave drag did. And so, yes, it was expected, it's spot on the number, but should I rebalance the model? So that's a major question now. And for that, the question is, what happens to surface air temperature? I showed you the equivalent plot of the net radiative balance, and you see that the coupled model, the publicly available coupled model is there. Our generalized is the yellow line, so it went even colder than the prescribed ones. And it is now recovering after like 60 years. It's maybe halfway through between the two lines. So it's a hard decision. It's not easy to tell whether you need to rebalance this model or not. You might need to rebalance it, so probably this yellow line will not go that far down in its attempt to equilibrate. And but it's a judgment call. And in case you want to rebalance your model, there are instructions in the paper that will show up pretty quickly. But you should always consult with us. It's always the best advice. And
I guess it also depends on the science case, like we always say. I mean, if we're talking about exoplanets, does half a degree really matter, given all the constraints that we have or don't have?
And thanks for intruding, because I really forgot something I wanted to say and you reminded me.
Good.
The science case is very important because if you want to rebalance your model, you need to know whether you have a baseline to rebalance it. So in our case, we're simulating Earth with some more generalized physics. So we have the sea surface temperatures to balance against. If you are only making this change and you want to go into another planet, then you have no idea what's your radiative balance is. So you should not rebalance, to be honest.
Right. I think that's a really key point. Yes.
And
so what do you mean by rebalance? Just tweak the parameterization or okay.
Yeah, you basically try to balance toward a given sea surface temperature, right? That's what we do with the Earth model.
Exactly.
But if you don't have a canonical example of what you want to balance toward, you can't do it.
Right.
So you just leave it. It's half a degree.
Right. Yeah.
So
Yeah, so
that is for CMIP 6, but doesn't matter for what we do most of
Right.
the time.
Yeah, so the important thing is that stop my here. So the important thing is you need a mod for a model to be usable, to be bold, is you need to be close to radiative balance. If you want to take this configuration of the model, whichever it is, and it has an energy imbalance of like 9 watts per meter square, your model will explode eventually. It's just too much. So what we did is that we took our already balanced simulations, which are the pre-industrial ones essentially, and we changed the configuration. And then when we reached into, so this, if you read this plot moving to the right, you're essentially removing different things, and eventually you remove many things at once. Right? And when you reach into a configuration that is usable and not an intermediate configuration, we balance that. So we essentially change some cloud parameters that affects the cloud fraction and cloud type and stuff, and then we bring it back to 0 because we know that we assume that the planet at pre-industrial times was in radiative equilibrium because the greenhouse gas forcing or any anthropogenic forcing was too small to matter on a planetary scale, probably. So
those are the best parameters.
yeah,
to
so
tweak
we take
clouds.
it's the easiest way to change the planetary albedo.
Right. Okay, 3 minutes.
0 minutes. I'm done. Thank you.
Okay. Hopefully we see this paper published.
Yes, the paper is the text of the paper is there. A couple of sections that are not written, I'm taking them out. Time is up.
Good.
I am simply need to create the assets to be ready with submitting it. Restart files and stuff and submit it. That's it. Okay. Paper is ready.
So we've done a million experiments, and this is great, but I think sort of like the next step, something that like future climate people would certainly expect, you would know this, would be whether the sensitivities are the same. Like, so for example, we know from past versions of the GCM, the sensitivity to double CO2 of the fine grid is different than the medium grid. And you'd like to know that based on, when you're doing climate change simulations of other planets or paleoclimate stuff, whether or not by just changing something as simple as the resolution alters your answer. And, so picking a few of those experiments and doing sensitivity experiments and then publishing the sensitivity of the model.
I think it depends on the setup. I mean, in our Archean paper, I did a couple of high resolution runs just to see what the difference in the global mean surface temperature was from some medium resolution runs. And the global mean temperature was the same within half a degree. I thought that was pretty good.
So this shows sensitivities though. This comparison is essentially that.
Right, it's a sensitivity to physics changes in the models, not necessarily a sensitivity change to something like atmospheric chemistry.
Right,
but it's ready to be done. Yes, I agree with you.
I completely want to stress. I mean, like in some future study, not as something additional that needs to fit into this, but. It surprised people in the past, right? That even when they had tuned versions at different resolutions, and I suspect this would be true of different radiation codes, for example, that then suddenly the sensitivity of the model changes.
Okay, one quick question for Andrea, then we'll move on.
Just curious what it changed the cloud atmosphere. Was there a number?
So the Earth model is having something like a map. I don't know if it's literally a map or something like that, but it's something that is using information from where the clouds are and how they look like in terms of the microphysics. We don't have microphysics in the model, and we don't have the cloud fraction does not tell you anything about how inhomogeneous, whether it is a big cloud or several smaller ones in one grid box. So it uses information from the real Earth on how to do that. So I took this out and I added a number which is 0.14. I have no idea what this number is, but it's the generic number that we are using. We are using a generic some generic parameterization of the clouds. So I think this is the global mean of Earth still. So of some variable, and again, I'm sorry, I don't know what this number exactly is, but it's a global mean that came from present-day Earth. So we assume that, globally speaking, then homogeneity would be about that, and use that everywhere instead of imposing something, because that will affect your local albedo.
I'm pretty sure.
Okay. We take it offline. Sorry, we have to move on. Thank you so much. Okay, can you stop sharing this? Okay, our next speaker is Avi Mandell. Avi is one of the 3 people we have from Goddard talking this week. And I thought it'd be really cool to hear about this mission concept that he's working on. Mostly because whenever I hear people talk about HWL, my eyes tend to glaze over because it's going to fly when I'm either well retired or dead. This is something that might fly well before then. So I thought it'd be really great to hear about this mission from Avi. So Avi, just to comment, last time when you were introducing yourself, your voice was cutting out a bit. So maybe keep your video off. I don't know if that will help. Let's see how it goes. I might have to interrupt you to tell you to fix your audio.
Okay, how about now? Do you hear me okay now? Or let's see if I can
still breaking up. It's still breaking up a little bit.
Yeah, let me see if I have the microphone correct here. Oh yeah, the mic. Okay, how about that? Is that better now?
That's much improved. Thank you so much.
Zoom had the wrong microphone from the laptop.
Naughty Zoom.
Naughty Zoom. Okay, great. Can you see the slides now?
Yes, thank you.
Excellent. So yeah, so as Mike said, this talk is going to be specifically about this mission concept we call MIRECLE, the M-STAR Infrared Exoplanet Climate Explorer. And the goal of this mission is really to be complementary to some of the primary 600-pound gorilla on the horizon for us, which is the Habitable Worlds Observatory, because as is in the title, this mission is meant to really be sort of a follow-on mission to the James Webb Space Telescope, which has been doing spectacular work, early work, initial reconnaissance on small rocky planets around M-stars. And the goal for this mission would essentially be to try to take that type of work to the next level, to focus, to push down towards temperate terrestrial planets, and again, expand the sort of range of potential targets that could be accessed compared to what James Webb can do by focusing on non-transiting rocky planets, as well as the few golden targets that we know of that transit their parent star. So I'll start out, with this, just, since this is kind of a diverse crowd, lots of people from, earth science backgrounds with, sort of more GCM heavy focus. I want to start by talking about what we colloquially call the M-STAR opportunity in exoplanet studies. First, let's talk about why we care about habitable zone planets around M-stars. One astronomer called these guys the angry little red devils when talking about red dwarfs, because they're really not necessarily friendly places to have planets around. They're very active. They're heavily biased towards the red portion of the spectral energy distribution. They can be misbehaved in a number of different ways. But the key factors are when you start to compare them in an observational sense to our own solar system. So G stars, which here are on the bottom, and then K stars and M stars. This progresses towards cooler stars at the top, so smaller and cooler stars. But you can see that there's a number of sort of benefits of the small stars, which is primarily that they're smaller, and therefore the planet-star flux ratio is dramatically more favorable for detecting either the emission or the gravitational polar or the effects of a planet overall on the planetary system observationally. And second, they're much, much more abundant in the universe. The stellar mass fraction, rises exponentially towards smaller masses of stars. And so if you look in the nearby solar neighborhood, you're going to find way more M stars, especially the coolest M stars, than you will G stars, and even K stars. So those are the positives. Of course, the negatives, as I mentioned, are the, most M stars have much more UV and X-ray radiation irradiance than G stars. You can see here a sort of average factor of 400 over cumulative XUV over their lifetime. And this question of longevity is an interesting question. Does that help you or hurt you in the overall sort of expectation of the presence of an atmosphere or potentially habitable environments? And then there's other factors that you guys know well, things like especially related to the orbital period of planets in the habitable zones of M stars. Orbital periods of habitable zones are on the order of 10 to 20 days. And so I'm sure you'll hear a lot about that, what that means for the overall global circulation of the atmosphere and volatile circulation and so forth. So really interesting. I like to think of habitable zone planets around M stars as planetary extremophiles in the kind of astrobiological kind of terminology. We're really, of course, we would be pushing the bounds of what we think are clement conditions for life on Earth. And therefore, as we examine these planets for atmospheres and signs of life, we're really asking, can life form and survive in more challenging and different environments than we see on Earth? So, of course, raise your hand. I don't know if I can see anyone in the room, but Mike, you can jump in and tell me if there's a hand raised with a question or anything.
So I think we're good. Keep going, Avi.
All right. So to this question of the abundance or the presence or the closeness of planets around nearby M stars, this is a plot of the known planets around stars, all stars within 20 parsecs. So you can see on the bottom is a distance scale out to 20 parsecs. And then on the y-axis is the stellar insolation. So this is the amount of flux relative to the Earth, bolometric flux received by the planet. And then the color coding is the spectral type of the parent star. And then the size is Mars mass all the way up to Neptune mass for the largest planets plotted here. And so you can see that as you go to larger orbital distances and therefore lower stellar insolations, the known planets around the nearest stars are heavily biased towards the coolest spectral types. And this is purely a selection, a combination of a selection bias that those planets are easier to find, and also just an abundance bias that many more of the nearest stars within 20 parsecs are going to be K and M dwarfs versus G-type stars. And so if you hone in even more on what you might consider the optimistic habitable zone, at least for sun-like stars, this kind of Venus to Mars insolation regime, you can see that these ones are biased almost exclusively into the M dwarf regime. And that's, again, sort of honing in on planets that can be discovered in short orbits around the nearest stars with small planetary radii and mass. And so if you sort of point out a few key targets, Proxen B, which everyone's familiar with here, is that one on the far, far left. That's the sort of highest of the highest golden targets for non-transiting planets around M stars. And then the TRAPPIST-1 planets are these 7 dots all around 12.5 parsecs. Everyone, don't have to talk about TRAPPIST-1. But the interesting thing about TRAPPIST-1 is these are the only known transiting habitable zone planets around an M star or at all within 20 parsecs. to us. Those planets transit their parent star, and all of the rest do not transit their parent star. And so you can see that as you get out to these orbital periods and installations, there's an additional sort of probability factor that drives you to be very interested in non-transiting planets because of the geometry that drives that probability. Okay, so of course, then you get to the big question: could planets in the habitable zones of M stars actually be habitable or even inhabited? And Rory in the room there could speak to this wonderful figure from the VPL team much more than I, but there's been a lot of course, interest and study in the recent years about what the different types of atmospheres might be on planets around Mdwarfs. And there can be, I won't go into this again too much here, but there's a lot of different pathways and directions that a planet could take under different initial volatile conditions and XUV environments and so forth. And so there's so much unknown about these types of planets. And there's a huge discovery space to be explored if we can. All right, so that's enough of motivation about astrobiology. But the first question we have, even before we get to the question of life, is can M-star rocky planets even maintain a secondary atmosphere, primary and then secondary atmosphere, or any atmosphere at all? This is a classic figure, or infamous figure, some might say, from Kevin Zonley and David Catlin in 2017, which they call their cosmic shoreline figure. This is showing for all the bodies both within the solar system and the known exoplanets at that time, where planets fall based on their mass, which drives their escape velocity on the bottom, and then versus their XUV irradiation level, cumulative XUV irradiation. So I sort of want to point out that when you get to the question of cumulative XUV irradiation over the lifetime of a body, it's huge uncertainties are implicit in there. But you can see that there's this empirical relation that sort of may separate planets or bodies with atmospheres versus those without atmospheres. And then you can see all the exoplanets on the upper right with almost no information at that time. And this was recently updated to at least look more slick and well-defined by the Space Telescope Rocky Planets Director's Discretionary Time Program. And these are all the known transiting M-dwarf planets, or the nearest ones, laid out on this plot. And you can see that atmospheres are more likely to the bottom right and less likely to the top left. But again, these beautiful green and blue lines, are extremely model-dependent ideas or sort of boundaries where you may or may not see a transition from bare rocks on the upper left down to planets with atmospheres on the bottom. So this is the type of sort of broad demographics that really motivates sort of a large survey, a study of planets around M-dwarfs from the Mercury regime all the way out to past the Earth regime in order to sort of define where planets have atmospheres and where habitable environments may exist.
So Avi?
Yes.
On this Space Telescope one, that's just insolation on the y-axis. So it's a very different quantity from cumulative XUV flux.
Yep, exactly. Yeah, I grabbed the figure from Kevin's paper that specifically had XUV flux. They also had one with insolation, which, as you said, is a very different, driver factor. This is the only one that was published by this Rocky Planets team. Again, Rory's on this, the science advisory panel for this DDT program, and we should ask him all the new work that's been going on to try to define the priority of planets in this sample. But it's a really great question of where you might expect this transition to happen based on these various factors.
And I see TREPPIST 1b in the right is at the friendly side of the line. just to point out.
Yeah, yes. There's D, there's C. I'm trying to find B. There's a little busy here. Rory, did you want to add anything since we're in a, cozy
Sure.
space?
Well, yeah. Right. So I will say we did just put out maybe in the release last week a figure like the one on the right that is cumulative XUV irradiation. I also mentioned that I did run an experiment with one of the candidates, GJ1132P, and I think the uncertainties on the y-axis there are about a factor of 10. Roughly speaking, maybe it's more like a factor of 30. And then it's not, and part of the priority schemes that we had, and I can look back at the Slack message that came out yesterday, but we tried to articulate that because I think there's some questions about the initial choices that we made. But there's also factors of like, do we have RV data? Do we know the mass of these planets? Just how much time does it actually take to maybe observe an atmosphere based on the height of the atmosphere that's predicted, basically scale heights. So I think that this cosmic shoreline idea is what's kind of motivating this from like a theoretical side, but there's also a lot of other factors just from the observational side that go into prioritizing candidates for this survey.
Exactly.
Yeah. Helps clarify anything.
Thanks, Rory.
Well, he thanked me at least. I'll be thanking
Yeah, so I'll continue on because when we're talking about this survey, this great sort of detailed, descriptive, like heavily intensive focus for the DDT program that people are talking about here with this figure on the right, this is the data that we are expecting that we would get for those observations. And so this is the type of emission, thermal emission observations at 15 microns that survey would acquire, which is a single data point. Essentially, it's a photometric band that is observed uniquely over a single eclipse, essentially. And so this was for TRAPPIST-1c. This was one of the first sort of demonstrations of this method. And this was 4 eclipses. And you can see here that by measuring the difference of this point from the black body, you can see there's a 430 Kelvin black body and a 340 Kelvin black body, depending on whether you have a instant re-radiation, aka no atmosphere, or some atmosphere with redistributing of heat from the day side to the night side. This data point would move up and down. And then you could have CO2 absorption, which would also diminish the flux from the planet at this wavelength, as you can see here in this purple figure on the right. So you can get a really sort of intriguing initial sort of idea of whether there is any type of atmospheric indicator from this spectral point. But you're incredibly limited because of the wavelength coverage of the MIRI instrument in the beyond 11 microns. There's no sort of stable spectrographic mode available with the MIRI instrument beyond 10 to 11 microns, beyond the LRS mode with MIRI. And so you have to do these photometric measurements one at a time across the infrared. And so this is the biggest motivation for saying, what would we rather do? What would we like to do beyond 10 microns if we had a new mission and a new instrument that could be designed specifically for this? There's other factors that make JWST, sort of more limited. If you're focused on transiting planets, as I mentioned before, you're limited to much more distant targets, just because of the fraction of habitable zones that transit. And you can use transmission spectra, which people have really focused on in the first few cycles of JWST. And I won't talk about that here because that's not the focus of the MIRECLE mission right now. But transmission spectra have its own sort of challenges in relation to sort of the limitations of that type of observing strategy. And so JW is doing great initial reconnaissance, but it would be sort of revolutionary to be able to take this to the next level and explore these planets in more detail. Just a brief point about the Habitable Worlds Observatory and the ELTs. The idea of these missions would be to actually image planets around the nearest stars. HWO will use direct imaging with high contrast coronagraphy, and the ELTs will use similar, maybe sort of related, including high resolution spectroscopy. There's a number of different ideas. But there's a fundamental limit to imaging systems, which is that you have to block out the central star, and your technology for doing that leaves this black hole in the center of your image called essentially the exclusion zone, or the inner working angle of your imaging system. You can see that on the left with this simulation of the Habitable Worlds Observatory. And if you plot the target list for HWO, here on the right, this is Mamachek and Stapelfeld 23. This is a preliminary target list. You can argue about the specific targets, but you see that dotted black line showing this exclusion zone here as a function of distance to this targets on the bottom, and the luminosity, aka the spectral type, on the left. And you can see that these are all focused on the habitable zone of these stars. And the habitable zone gets so close to its central star as you go down to M stars, and especially late M stars, that you really can't image the habitable zones of M stars, especially at long wavelengths. So what do we do here? How do we move forward onwards? So we have this new strategy we call planetary infrared excess. You can sort of put it on this continuum of three different kind of axes for detecting the sort of signal or distinguishing the signal of a planet from its star. You have direct imaging on the upper left. I won't really talk about that anymore. But you have transmission and eclipse spectroscopy on the right, and they both use either spatial differentiation, as you can see in the image plane, or time. So watching the planet disappear or affect the stellar signal and differentiating the star and planet by looking at those in time. If you add the wavelength dimension here, you can start to add this differentiation by looking for the excess emission from a planet over the stellar emission versus just the star itself at short wavelengths. And that's because the planets are cool, 300 Kelvin, 400 Kelvin, while the stars are 2000 Kelvin and above, all the way up to 3000, 3500 Kelvin. And so you can differentiate the signal of the planet from the star in wavelength in this sense. Now, that's challenging to do. You have to use a lot of different tricks of data analysis, benchmarking at short wavelengths and comparing to long wavelengths. I'll talk about that. But in theory, you can combine the evolution in time of your planet over its phase, as well as the differentiation in wavelength between the star and the planet to extract the signals. So we sort of took this toy model and we turned it into actual, sort of a retrieval analysis study where we actually did noise models of different types of observatories. We published this in 2022. You can go sort of check out the paper for all the details. But the proof of concept was basically looking at the Proxen-B planet for 100 hours, which would essentially be 4 days of observations. And showing that even with a 2-meter telescope, you could extract a high SNR spectrum in the mid-infrared for a Earth-like atmosphere for Proxen-B, if that exists. And we actually made an attempt to constrain the different molecular species you might want to detect. And you can see that CO2 and O3 are especially detectable, and that's because of their positions in the mid-infrared, the spectral bands. CO2 is obviously broad and relatively easy to measure at 15 microns, and then the O3 band at 9 microns is also accessible. But what we also found was that H2O and CH4, because they make such an impact on the short wavelength side of the thermal emission black body from an Earth-like planet, you can constrain the water vapor. And what you're doing is measuring water vapor close to the surface where the atmosphere is densest. And so it's quite different from what you expect from a transmission spectrum, where you're measuring the atmospheric species abundances high up in the atmosphere. Here you're looking down deep into the planet's tropopause. Now, of course, this has lots of caveats. First of all, didn't include clouds. The cloud caveat is always a big one, but it was an initial proof of concept to show that at least that from a signal to noise level, a 2-meter telescope should be sufficient to constrain at least this high value target. And then we did survey sensitivity studies of the wavelength range required, showing that 2.5 to 18 microns would be sufficient to do this type of study.
I'll be 4 more minutes.
Yep. So how do we remove the stellar flux accurately? We've been doing a lot of different strategies focused on phase curve analyses. Here you can see that if you calibrate your spectrum in the stellar region, this is work done by Ted Johnson, now a grad student at UNLV. You can remove the stellar contribution at short wavelengths, and then you can reveal the phase curve of the planet and fit for the day and night sort of spectra and composition factors just from the phase curve with no transit in the data set. So that opens up, of course, all the targets that I mentioned, the closest to Earth, especially within 5 to 7 parsecs of Earth. And you could, and the goal of that type of phase curve analysis would be to produce this type of 2D, pseudo 3D map of your planet as a function of phase within spectral features, searching for constraining the abundance of water, carbon dioxide, ozone, and so forth, and the temperature across a planetary surface. So how many planets could we do? So with a 2-meter telescope, this sort of shows a lot of different histograms. I don't have to go into all of it, but it shows that there's this golden sample of planets between sort of 200 to 350 Kelvin equilibrium temperature, where you're accessing, on the order of 10 potentially habitable planets around the nearest M stars and rocky planets, as well as a number of sort of warm Neptunes, which, similar to K2-18b, may pose interesting astrobiological targets as well. And then moving up into the Venus and Mercury zone as well, many more targets, and up to mini Neptune targets in that regime as well. And so, we have I didn't put a lot of technical slides in, but we have this whole observatory concept of a 1.5 to 2 meter telescope, heritage from JWST and the Ariel mission. And we have a SAT, is Rose's proposal right now to demonstrate the instrument operating from 1 to 18 microns with a 5 parts per million, better than 5 parts per million stability goal. And all of this uses high TRL technology that we should be able to propose for the next mid-X opportunity in 2028, ready for a launch. Oops, I seem to have cut off the launch date, but in the early 2030s would be the timescale for launching this mission. So we're now within the sort of 4-year window, which we're raising TRL levels, defining the science case, and continuing to demonstrate the data analysis and observation strategies with JWST and other missions. We do have one other thing, which is a potential new aperture technology, which was proposed for the Saltus probe class mission, which would dramatically increase our telescope size from 2 meters all the way up to 8 or 10, or even all the way up to 14 meters in size. This is a technology that would be extremely lightweight. You would essentially inflate a membrane with helium and then crystallize it as you cool down to a sort of a semi-parabolic surface sufficient for light bucket spectroscopy in the mid-infrared. and cold at 40 Kelvin, exactly what we need, radiatively cooled to 40 Kelvin, exactly what we need for this mission. But we're waiting on the outcome of the Apex Phase A selections, and we're continuing to sort of include this now in our potential sort of range of aperture classes, showing that how powerful it would be for known transiting planets, in or near the habitable zone of M stars. Here's LHS 1140b with a warm Venus atmosphere at 290 Kelvin, showing that with a single eclipse, one eclipse, a 14-meter telescope could get a spectacular spectrum, showing the CO2 and ozone bands. So finally, I'll just leave this up. Sorry I took a little bit longer, but let me know if you have questions. Here's where we are. We're moving forward on the science case development. So if you are interested, ROCKE-3D team, in helping to think about M-star habitable planets and what we might expect under different scenarios, we want to do hypothesis testing for planets in different temperature regimes and mass regimes, thinking about specific targets that we might want to focus on. And then finally, developing, of course, the whole overall key science drivers and the design mission concept, specific targets. So there's a lot of work to do, and I'd love to have your help. So please let me know if you're interested.
Thank you, Avi. Really great. Of course, we don't have time for questions, but you can write in the chat window. Thank you so much, Avi. That was really great. It was exactly what I was hoping, and I hope people will reach out to Avi, and we should definitely work with him on this. I think it's a great idea. Thank you so much. Okay, could you stop sharing, Avi? And then, Jen, are you there? Yes, I see you. Okay, so our next speaker is going to be Jen Carter. This is a project we've been working on for a few years since she finished her PhD thesis with Kevin, who's in the room with us. And take it away, Jen, and get your stuff up here.
Should be able to see the screen now.
Yes, looks good.
Most excellent. Thank you. All right, thank you for having me. I'm going to talk about how we might account for the finite angular size of stars in considering the illumination of exoplanets. The motivation here is planets that are very, very close to their host star do not experience the illumination that we usually model for with plane parallel rays. They end up with excess illumination, sometimes extending far beyond where you normally would think the terminator is located. And this might affect things like the amount of expected reflected light from the exoplanet in the case of photometric measurements. And it will probably affect things like your energy balance equations when considering the energy budget of the planet. What I want to start off with today is just taking a look at kind of a big picture of illumination. And then we're going to get into some math for illumination and finally some illumination maps for two exoplanets that I just decided to look at. First, looking at illumination kind of in bulk, the plane parallel ray model is assuming that the star is far away so that you could not just treat it like a point source, but a distantly located point source. So all of its rays hit the exoplanet like they're plane and parallel. You can almost think of it as a sheet of light smacking into your exoplanet. This leads to two main illumination zones, right? We have a day side and a night side. This would imply that the star sets instantly at the terminator, and that the terminator would be located along the hemisphere of the star, the planet, excuse me, facing the star. So if we take the substellar point as our 0 point for longitude, then the terminator is located at 90 degrees longitude, positive and negative, and runs through the poles. But if planets are very close to their host star, we might have a situation looking like this, which is a little exaggerated. We have our star on the left and our star on the right. And at these close separations, the star is not a point source. It has finite angular size in the sky of the planet, sometimes very large. This leads to three primary illumination zones defined by tangents between our spherical star and our spherical exoplanet. We're assuming they're spheres right now. The fully illuminated zone is the most like the day side, located here in yellow between these inner tangents. Points here receive light from the full apparent disk of the host star. This is actually formed by a spherical cap of the star facing the planet, and it's not the full hemisphere facing the planet. It's always a bit less. Next, the outer tangents are actually what define your terminator now. Any points beyond these outer tangents here are in the unilluminated zone. And this can extend very far beyond what you would normally expect, some as far as 20 degrees. Finally, between the two, we have the penumbral zone that I've split into two. The near one in orange, the penumbral zone 1. Any point that receives light from more than half of the apparent stellar disk, but not the full disk. Any points beyond there in this maroon area receive light from less than half. I split these two zones up because in the course of my thesis, I discovered that there were some important changes to the integration required for determining the light here that occur at this line. Basically, there's a sign change that cannot be ignored. Now that we've looked at kind of a bulk idea, I want to look at what we would expect from the illumination for the plane parallel array case. Then we're going to discuss how we be a bit more precise. So this is an illumination map for Kelt 9b, which is a hot Jupiter. And I just want to go over what's shown in this plot. We've got longitude along the bottom in degrees, latitude along the top. The color code is given here. Here's our color bar, and its intensity in parts per million of the intensity of the host star. So we've normalized to the host star. At the center, we have the substellar point. That's our 0, point. And there are some key features to look at here. With plane parallel arrays, we have a very sharp terminator here and here at -90 and +90 degrees longitude. And we have a maximum at the substellar point, and everything decreases according to the cosine of an angle. It's the angle between our substellar point and whatever point you are on your planet. And I have another figure to show that. Well, Kelt 9b is only 3.1 stellar radii from its host star. And with that, it ends up being that the finite angular size becomes quite important, and we're going to build up to that now. First, a little bit of geometry, just so we can understand what angles we are talking about. I have the star on the left and the planet on the right, and I just want to draw your attention to a few key features. We want to know how much light is received here at some point P on the planet from some point Q on the star. And then we add up all of the Qs that are visible at the point P, and that's our total incident radiation. It's going to depend on a few things, and that's what all these angles and distances are for. Important here, we've got rho prime. This is the vector from P towards Q. So it's the separation between our 2 points. P hat here is the normal of your point P on the exoplanet. dr hat Q here is the normal for Q. This D is here just because I was thinking about vector addition. So if we take our origin to be the center of the planet, we have our star-planet separation here, plus dr gets us this separation between Q and the center of the planet. This is helpful depending how you want to set up your integration in your code. Another important angle I want to point out is gamma prime. That's that cosine of the angle between your substellar point and point P that we saw on that last slide. That's what sets up the loss of light as you move away from the substellar point in this model. And for large star-planet separations, this works great. But for close by ones, we need to be a little bit more careful. And here's our basic setup. The differential incident light at P depends on the light from Q. So that's this guy. But it's also projected towards P. So we have this angle between the normal of P and the line connecting P to Q. So instead of gamma prime, we're concerned with this angle here, psi. And our strategy then is to add up all the Q's in terms of the solid angle subtended by point Q as viewed by point P. And for the plane parallel array approximation, you can make some simplifications and we get our usual result. But here we're going to be a little bit more choosy about what we simplify. To start, we're going to assume that the intensity from each point on the star is the same. We can easily modify this for any limb darkening law we really want, but to get us started, we're just going to keep it constant. And then I want to talk about that solid angle at Q, of Q at P. For this, we project the surface area of Q towards P. This is that projection. That's why we need to know the normal of Q and this vector here connecting P and Q, as well as their separation squared. That's down here. The minus sign is just accounting for the fact that these two vectors are in opposite directions. Let's just bring it all together now and get a look at what we really care about. What's the differential light received at P from Q? Combining terms and using cosines, we get this. All right, depends on light, intensity, separation squared, the surface area, that's our integration, and these two cosines. This one, cosine theta prime, projects Q's surface area towards P, and then cosine psi projects the light coming from Q onto the normal of P. If we do this analytically, we don't need this max function. We just set integration limits appropriately. If we do this numerically, then that max function serves to set this to 0 for any time that one of these is negative. Because if cosine theta prime is negative, Q can't be seen by some point P. It does not contribute to the integral. If cosine psi is negative, then P is too far over to receive light from Q. It doesn't contribute to the integral. So we just set the intensity to 0. There are other ways to do this. This is just how I'm representing it here. Well, some of this has already been done, and we do have solutions that are analytical in some regions, and we have some that are not. Let's talk about that now before we look at some maps. The integration is zone dependent because that changes the limits. In the penumbral zone, which is shown here, we have some point P. Its horizon cuts off the stellar disk at some point H. We have to account for that in this model. And what we want to do then is integrate from here all the way to this tangent line. That's the part of the sphere that's visible. This is penumbral zone 1, where more than half is visible. So H is below this line here. In the second zone, H is above that line and less than half of the disk is visible, just from here to here. Within the fully illuminated zone, this horizon doesn't intersect with the disk at all. The integration is straightforward and doable. We have an analytical solution in that fully illuminated zone, shown here, in units of stellar intensity. It depends on cosine of an angle alpha, which is this angle between the normal and rho, which connects P to the center of the star, and of course rho squared. Importantly, what I want to point out about this equation is I've hidden a lot of things in it, all of which depend on the location of P, so its latitude and longitude, the star-planet separation, and the size of the planet. And that's it. And then we could calculate the intensity of light received at points in the fully illuminated zone. Unfortunately, this doesn't appear to be the case within the penumbral zones. It is not an analytical solution that is exact. We can use approximations and do like some sort of series expansion, but there isn't an exact solution that I have found. So instead, in this talk, I'm going to be presenting numerical results, where I've taken 5 source points and put them on the hemisphere of the star facing the planet, and we're going to add up the light from each. We're going to see what happens. All right. Finally, we're going to use our analytical solution to test how well our numerical solution works in the areas of the planet that it applies. Okay, so Kelt 9b, illumination maps. On the top, we have the results using our numerical method that accounts for finite angular size. And on the bottom, we have the plane parallel ray approximation I showed earlier. The yellow dashed lines mark that traditional terminator. Few key differences. There's greater intensity of light received at the substellar point in this numerical method that accounts for finite angular size. Quite a bit more, tens of parts per million. There's a more gradual decrease in loss of light as you go towards the terminator. And most importantly, this contour line here for 0% light is well beyond that traditional terminator. This actually extends to 17 degrees beyond the poles. Now, what about something that's further out, a planet that has a much larger star-planet separation? Let's look at TRAPPIST-1d, which is about 39.5 stellar radii from its host star. We see some of those same features, right? But importantly, the maximum illumination is much, much less at only 0.7 parts per million. Instead, before it was something like 220 parts per million of the intensity of the host star. Now the plane parallel ray method, strangely, predicts greater substellar illumination. But our numerical method that accounts for finite angular size does still predict illumination beyond the poles at about 1.4 degrees beyond. Couple of things I want to say before wrapping up. Here we're looking at the intensity equator, and I'm looking at model subtractions because I want to test how well the numerical method of integration I'm using matches the analytical solution in the place I have it, that fully illuminated zone. The intensity equator is at latitude 0, and we're just looking at all of the degrees of longitude. The fully illuminated zone exists here between these green dashed lines. So that's the only place you're going to see any solution related to that zone. The unilluminated zone starts at these black dashed lines, and the red dashed lines mark -90 and +90 degrees longitude. I first want to talk about this subtraction in the middle. The difference between our analytical solution in the fully illuminated zone and the numerical integration in that zone, shown here in the blue dot dashed line. It's close to 0 parts per million, but not quite. This is why the difference between the fully illuminated zone and our plane parallel ray approximation is not directly on top of the difference between our numerical integration and that plane parallel ray approximation. That accounts for that little bit of difference. And here we see that difference in substellar radiation right here. We see a more gradual loss of light as well. As we head towards the terminator, eventually the plane parallel ray approximation predicts more light than our numerical method. Eventually, that amount of light starts to decrease. Here, we hit 0 light from the plane parallel ray approximation. And we have a difference of 10 parts per million here. Gradually, then, there's no light as we reach the terminator for Kelt 9b. Do these features exist within TRAPPIST-1d, which, again, much larger star-planet separation? Not exactly. The difference between the fully illuminated zone and the unilluminated zone is much tighter. And we see now that the fully illuminated zone is better approximated by the plane parallel ray approximation than our numerical integration. The differences are extremely small, though. So what I think is happening is that the amount of light received at this large separation is on the order of the numerical precision of the integration, not of the machine, but of our integration method. So will increasing the number of points help us? Instead of using 25 source points, maybe we should use 100. And that's what I'm about to look at next. Here, we're looking at the intensity of light for Kelt 9b and TRAPPIST-1d in parts per million of the stellar intensity along that intensity equator. Each of these dot-dashed lines are colored for a different number of source points. Our fully illuminated zone analytical solution is the black solid line. We want these guys here to be on top of that line. We have a pretty good fit if we just use one source point. But then we lose all of this cool information here in that penumbral zone. The fully illuminated zone doesn't apply there. Also, I noticed that we don't get much improvement as we increase the number of source points. The difference between the two models is always non-zero. And this, to me, points to a need for a more precise numerical integration technique to improve this analysis, especially for planets that don't receive a lot of light. Wrapping up, again, that numerical integration compared to the fully illuminated zone, it's not perfect. The difference between the two never approaches zero. The fractional difference between the two, that analytical solution and the numerical approximation, increases with star-planet separation. The fractional difference does. Again, pointing to needs to improve our integration techniques, but there's a lot of excitement to be had. The finite angular size of stars is very important for our close-in planets. It significantly affects that illumination profile. We have illumination extending far beyond 90 degrees longitude, both plus and minus. We have greater illumination at that substellar point, and we have a more gradual decrease in illumination than the standard cosine law that we usually use in that plane parallel ray approximation. My big question that I'd like to take a look at over the next year or two is how will this affect things like climate models, atmospheric models, looking at that energy balance, as well as the output, like the expected reflected light of exoplanets. With that, thank you for joining me. I have some slides to answer questions, as well as I can go back or forward. Any questions?
Thank you, Jen. You do have time for some questions. Chris?
I just had, you said you're going to get into how this matters for climate, but just can you make a quick statement about just the global sum of incoming radiation? Because that's kind of the first thing we think of. If, does it add 10 watts per square meter to the global integral of what the planet's getting? Or
I don't have an estimation of that at this time, but it's something I could calculate, especially I'd be most confident in the calculation for things like hot Jupiters, less confident, or hot terrestrial planets, less confident for things that are further out from their host star. That I'd probably peg at less than parts per million. Things like very hot planets, probably in parts per million. We added it all up. I mean, at least 10 just from the substellar point. And then it extends beyond the traditional terminator. But the amount of light is small beyond there. So probably not too much more than the excess we get from the substellar point alone.
So I would presume that at least for some problems, one wants to know not just the total intensity of radiation, but also the spectrum that's getting received. And that will, depend quite strongly, because if you are only seeing, the edge of the star, then obviously limb darkening effects will start playing a role, and you will be cutting off your sort of shorter wavelengths radiation. Do you have plans for including these effects in the calculation? Because if you're doing all the integration numerically, you can just as well do it for the whole range of frequencies. by,
Yeah.
accounting for the limb darkening and so on. And then you would get a full, see how the spectrum changes in all these cases.
Yes. No, I think that'd be an excellent thing to add to this, is adding that limb darkening and then looking at this for each bit of light, like those different wavelengths in the spectrum of the star. That's just beyond what I've looked at so far.
It's adding another dimension. Yeah, frequency. We change the usual intensity being like a constant to being, the Planck spectrum or something. To start with.
Something more sensible. I have done limb darkening a little bit with the analytical solution for the fully illuminated zone with linear limb darkening. I haven't included Spectra yet, like looking at that other dimension. I think that's an important thing to do moving forward.
Nancy?
Thanks. That was actually my question too.
Sorry.
No. This is obviously there's interest in that. But to add to that, I didn't quite, I wasn't kind of caught up. I didn't get the quantitatively. What was the actual flux difference that you're getting around the terminator between your two models? And could that be translated into photon flux maybe?
So the difference, I think, if we look at for Kelt 9b, which is one I'm more confident in, the difference in parts per million between the fully illuminated zone, and I think maybe more interesting for you between
explain parts per million also. I don't think that's kind of for light flux.
It's something more used in light curves, looking at photometric variation from the whole planet, which is where I actually started my research. Originally, this was more related to the reflected light, and I've switched gears. Anyway, parts per million, basically it's fractional flux, and take each one of these numbers and multiply it by 10 to the minus 6. So it's parts per million.
Right, so it's fractional flux. Do you have the actual quantitative flux amount?
Not at this time. I'd have to basically multiply by the flux of the star, probably just normalize it to that substellar point. It's something I could do. I just have not done it at this time, and I can add that for future talks.
So are you going to work with ROCKE-3D for any of this? Okay, so Mariella also was here. Mariella just we've been talking about putting more spectral resolution into ROCKE-3D. So maybe that's something we can get together to talk about.
Very good. Okay. Rory, you had a question?
Yeah, I was curious about, it looked like from one of your equations that you were including the distance between a point on the star and the point on the planet. And I wanted to be sure that I got that right. And then I was also just curious if you were doing that, just how big of an effect is that? Like, can you just, if you just assumed that all the light came from a single distance, is that really an important part of the model?
It is an important part. So yes, I'm looking at the distance between a point on the planet and a point on the star. How much this matters is going to depend on the relative star-planet separation to the size of the star. For something like Kelt 9b, the separation between the center of the star and the center of the planet is, let me check my notes, 3.15 stellar radii. So from here to here is 1 stellar radius. And then we've only got 2.15 more to get to the center of the planet. So the amount of light received from a point here at a point at the substellar point, it's a lot different if you just don't include the fact that this point is an entire stellar radius closer than you would use in, say, that plane parallel ray approximation, which instead uses just RS, the star-planet separation. Because that equation basically just looks like this, except alpha becomes gamma prime, and rho becomes RS, the star-planet separation of centers. Does that answer your question?
Yeah, thanks. qualitatively, I was just kind of wondering for Kelt B9b, just, do you have a sense of like quantitatively how much that effect matters?
Oh, sure. Yeah. Let's see. That would be the difference between this numerical approximation and the plane parallel array one. So at the substellar point, it is a difference of 10 parts per million of the stellar intensity. So take that stellar intensity and multiply it by 10 times 10 to the minus 6. I'm sorry, I don't know the intensity of Kelt 9 off the top of my head.
Okay, thanks.
Okay, Nancy, go ahead.
So in ROCKE-3D, then how is the model treating different orbital distances?
It's just plain parallel.
Plain parallel.
Yeah. But it's funny that I mentioned this project to Gary, who's one of our oldest developers. He's been here since the beginning of the model development, and he was saying he was really interested in this because he said that in some of the Earth models, he thinks the poles are a bit too cold, and he thinks it's partly due to refraction, but this could also play a very, very small part also, because we don't take refraction into account for poles either, for example. So.
Yeah, because I think this will probably matter the most for very hot exoplanets and still could contribute to potentially habitable planets that are around Mdwarfs, since they're going to be closer. But in my experience, this model seems to matter the absolute most for things on the order of 3 to 4 stellar radii separation. But I do think the poles, you're definitely going to get more light using this finite angular size at the poles than you would using the plane parallel array approximation. One of the things I really want to do is, yeah, we're out of time, but one of the things I want to do is get the numerical approximation better for the purposes of anything that has a small amount of light to begin with. Yeah.
Great. Thank you so much, Jen.
Thank you for having me. I guess, how do I stop
absolutely.
sharing?
Okay, we'll take Jen, could you stop sharing too? So we'll take a break now for a half hour. There are some refreshments in the hallway here, and you can find the bathrooms if you haven't already. Right. Okay, we're going to pick up where we left off. And for the next half hour, we're going to hear from Viktor Sparrman about some work that we've been doing a couple of years ago. So Viktor, please share your screen and take it away.
Yes, all right. Let's get this going. Okay, here, let me know. Can you see it yet?
Yep, looks good. See if you can speak up just a little bit closer to your microphone, maybe.
Okay, nice. Yeah. Is that fine?
Yeah, that's better.
Yeah, okay. So here I'm going to be talking about our recent paper in AppJ and published in February that I did while I was still in Uppsala, right before leaving here for Copenhagen. And this is going to combine stellar evolution with habitability. Okay. So as a start, this might be, incredibly basic to start, but I just want to cover the basics still because it's going to be combining different aspects at the same time. So we have the habitability. We have a habitable zone as our classical measure of habitability, and we define the liquid water habitable zone as having liquid water on its surface as our criterion for habitability. And typically or classically, this is given as a range of stellar distances. But for our purposes, it's going to end up being more useful to give the habitable zone ranges in terms of installation, which we heard about previously, as an amount of starlight that you receive at some distance from the star in units of power over area. With our assumption of isotropic radiation, this becomes an inverse square law. And once you combine this with stellar evolution, this is the evolution of luminosity of a sun-like star. And when I say sun-like star, I really mean a solar analog. This is pretty much the sun we're talking about. This is how the future evolution of the luminosity of the sun is going to look like according to the Parsec Stellar Evolution Database version 2 from 2022. And we can see that at the red giant branch tip, at the very end of the red giant branch, we're going to reach luminosities that are 2,500 times larger than currently. So if we want to keep a constant installation, how far away from the star can we move? And if you do the calculations, you'll find that this maximum value of the orbiting distance of an outer world that still receives Earth's current day installation is roughly 50 AU. So what this tells us is that at some point in the future, every world orbiting a sun-like star between 1 and 50 AU will at some point receive Earth's current day installation. But then it's important to study how long that is, because that's informing us of how interesting these worlds are in terms of being candidates for habitability. Okay, and you may also have noticed that I mentioned liquid water existing on the surface as my criterion for habitability. So then we both need to have a surface and we need to have an atmosphere in order for there to be some pressure, so that, yeah, we can actually have liquid water on its surface that doesn't just sublimate. So then we are limited to two candidates. These are either outer moons, like those that we have in our solar system, or outer terrestrial planets. And the outer terrestrials come with an immediate caveat that we haven't observed any. There aren't any in the solar system, and we can't see that far out into different stellar systems if we want to probe these low mass objects as well. But this is sort of to still be able to talk about outer terrestrial planets. We look to population synthesis models for plant formations, and they appear to be not only there but very numerous. So we don't consider this to be a caveat. It's just a result of our current observational limits. We expect there to be outer terrestrial planets. They just happen not to exist in our own solar system. And for the moon's part, we also require the moons to have atmospheres, because that's how they end up becoming habitable. So even if a moon currently does not have an atmosphere, once it receives more installation, it might thaw and release its volatiles and retain this atmosphere, at least for timescales relevant for the time it stays inside a habitable zone. Okay, but there's also an effective temperature dependence to the habitable zone range, which comes from the fact that properties of the atmosphere, sort of absorption coefficients and so on, are wavelength dependent. And the spectrum, i.e. the wavelength, comes from the effective temperature if we have a black body radiator, which we assume the star to be. So then we get that the equilibrium temperature of a habitable world is going to depend on the effective temperature, even if it receives a constant installation. Okay, so the work we did is based on these parameterizations of the habitable zone by Kopparapu, which is going to be a speaker in, I think, 2 or 3 people later than me. But we base our work on these parameterizations. So we have the conservative habitable zone, which is this one-dimensional radiative convective model without clouds. Here you have the runaway greenhouse, that is the inner edge of the habitable zone, where all your oceans evaporate and they act as they become greenhouse gases themselves in the atmosphere as water vapor, and then this causes the equilibrium temperature to increase even more, and all your oceans evaporate very quickly, and then after that you get some water loss by photoevaporation. And then we have, on the other end of the habitable zone, we have the maximum greenhouse limit, which is a limit where you don't benefit any in terms of net radiative balance by adding any more greenhouse gases. Because at some point, adding more carbon dioxide to the atmosphere just ends up making the planetary atmosphere more opaque to incoming radiation than it aids it in terms of trapping the radiation that this that is emitted by the planet itself. We also have the optimistic habitable zone in the same paper, and we are going to focus the rest of this on the optimistic habitable zone. And this is an empirical observation that's then stretched to this parameter space of effective temperature as well. And this is, it's just to define the limits as those set by the installation received by Venus and Mars at prior points in time. And the reason we continue to focus on the optimistic habitable zone rather than the conservative habitable zone is due to this discrepancy that can be seen here between the recent Venus, the optimistic inner edge of the habitable zone limits, and the conservative ones. So here, this plots the effective temperature and the installation, and the installation axis is reversed so that this preserves the orientation of going to the right is further out in a stellar system. Okay, so the optimistic habitable zone lies very close on the outer edge, but very far away on the inner edge. And this discrepancy comes from, basically the recent Venus limit said that Venus hasn't had water for at least 1 billion years rather than having water. But there's also been the one-dimensional modeling is unable to account for the cooling effect of substellar clouds, which is even more important for slow rotating worlds. And since we don't assume a rotation rate, then we employ the optimistic habitable zone bounds as just a more lenient habitable zone definition meant to encompass this fact that we know that 3D models appear to have a wider habitable zone. Okay, and here we go into this earlier plot that I showed for the evolution of luminosity, and here I focused in on the aspects or the time part of the evolution, which is going to end up being interesting. So we have luminosity on the y-axis. If we instead take this and divide it by the orbiting distances of the outer planets of the solar system, we get the same plot duplicated. I mean, it's just going to be shifted vertically because we're dividing by a different orbiting distance. And I've also overlaid the edges of the habitable zone. And what we are trying to calculate then is the time spent inside the habitable zone. So Jupiter, for example, enters through the outer edge of the habitable zone here and becomes more illuminated. And then at this point in time, it leaves the habitable zone from the inner edge prior to the red giant branch tip. Okay, so the results here are, I'm first going to show you the stellar evolution track on an HR diagram. This is the parsec track then. And I've marked in cyan points in time where at least one of the outer planets of the solar system reside inside the habitable zone. And you can see that this is a continuous time where at least one of the planets spends inside the habitable zone, aside from the very, very peak luminosity at the red giant branch tip. After the red giant branch tip, we get the helium flash, jump back here, and then we get one of the planets inside the habitable zone again during the horizontal branch. And this accounts for roughly 5% of the star's total lifetime prior to the end of the AGB. And this fact that this is continuous and there's no gaps in between planets entering the habitable zone, this is from the fact that the width of the habitable zone is like a multiple of 6 or 7 in terms of installations. So as long as planets are not spaced further than the root of 6 or 7 away from each other, then you're always going to have at least one of them inside the habitable zone continuously. Okay, so this is us calculating the time spent inside the habitable zone, and specifically the optimistic time inside the habitable zone. And I used 2 stellar evolution databases, but let's just focus on the parsec one here in solid colors. So I've marked the orbiting distances of all of the outer planets of the solar system. And I should mention that when I say these names of the planets of the solar system, I'm not specifically concerned with their habitability, right? We don't consider the habitability of Jupiter to be a real thing because we have surface liquid water, right? It doesn't have a surface that has liquid water on it. So this is sort of a proxy to stand in for, or rather a shorthand to stand for the moons of Jupiter or an outer world or exomoon at the same orbiting distance as that of Jupiter, and also around a sun-like star. So we have multiple bar plots for these outer planets, and these show that they have not only one time inside the habitable zone, but sometimes a second. So here for Saturn, you can see that there's a first time inside the habitable zone of, I guess, 800 million years. Sorry, 80 million years, and then 1.2 million years or so. And you might have noticed it earlier if you were paying super close attention, but you can actually see this on this here plot, where after Saturn leaves the habitable zone prior to the red giant branch tip and is uninhabitable for a while, it actually drops back down during the horizontal branch and then stays there for its full duration. And this is due to the fact that the horizontal branch luminosity is essentially constant for our purposes. So this plot is sort of an intro to what we're really after, which is a more complicated plot. So I'm gonna try to walk you through it. This is the same thing plotted on the y-axis, this time spent inside the habitable zone, but now we're giving it as a function of orbiting distance rather than just having tick marks for each of the outer planets. So then when we have multiple times inside the habitable zone, I distinguish those as these non-continuous phases of habitability by stacking the bar plots of each orbiting distance on top of each other. So here at I guess 6 AU or something, we have a secondary time inside the habitable zone that lasts for this duration between these two. So we have light blue as the first time spent inside the habitable zone, and then dark blue as the second, and then light green and dark green if there are third or fourth ones. What you may notice is that there's a significant secondary time inside the habitable zone for planets at the orbiting distance near Saturn. I mean, on either side of Saturn, we get a significant secondary time inside the habitable zone. And specifically for Saturn and slightly outside of the orbit of Saturn, the secondary time inside the habitable zone actually exceeds the first in duration, which is interesting and hasn't been remarked upon, I believe, in prior works. We tried finding some. Outside of that, you can see that the time spent inside the habitable zone, I mean, this primary time, it goes down monotonically with orbiting distance outside of 10 AU, where these interesting effects stop happening. I mean, here where we have three of the same one. But in order to say whether a secondary time inside the habitable zone is relevant at all, we need to evaluate the water loss in between the first and secondary habitable phase, because this was spent inside the inner edge of the habitable zone. So you're going to receive way too much installation, and we denoted this as the runaway greenhouse limit, right? So then we move into water loss, and here I thank Sunny for guidance in these calculations. So we have that the entire oceans evaporate into the atmosphere, and then we get photoevaporative loss. And we calculate the energy limited escape rate, which is based on this XUV flux. We talked about this. I mean, this relates to the Sunley what is it, cosmic shoreline thing. For the XUV flux being the determining factor of whether we expect them to have an atmosphere or not. So you can calculate the number of Earth oceans that you lose by integrating over this escape rate between the 2 points of exiting your prior habitable phase and entering your next habitable phase. And this is also dependent on the mass of the outer world and also mass of escaping particle. So you can calculate the number of Earth oceans lost for a few different masses, and I chose these to sort of represent the Moon, Mars, Earth, and some super-Earth. And we can see that the water loss goes down with orbiting distance because they spend a shorter time outside of the habitable zone before they re-enter. But you may also note that at most they lose 5 Earth oceans, which would be a lot for Earth. but it's not a lot for the outer worlds, we think, all right? Just based on our own solar system, we don't have any outer terrestrial planets, but even the icy moons, some of them have 40 times more water inventory tied up in ice and subsurface oceans than Earth does, despite being much less massive. Okay. Another thing that we want to do is, I mean, we calculate this time spent inside the habitable zone, and we say that this might inform us on sort of the likelihoods of origins of life and so on, but we need some comparison. And to do that, we consult the timetable of evolution, and specifically only this part here where they have, I think, a very nice indication of the origin of life. It's just a range, and we are very uncertain. So based on stromatolite fossil records, the life may date back at least as far as 3.7 billion years. Some say only 3.5, or it could be even 3.8. We have some difficulties in that the Hadean rock record is missing. I mean, it's extinct basically. But we have some other ways of probing further back. There was a paper in Nature 2 months ago tracing or trying to date the last universal common ancestor based on shared traits in remaining branches of life on Earth that date the last universal common ancestor to 4.2 billion years. So if water arrived on Earth 4.4 billion years ago or so, then it took at most 200 million years for life to develop from that point. Or it could have taken as long as almost a billion years if the origin of life was closer to 3.5 billion years ago. And what these numbers can tell us is, I mean, we saw this time spent inside the habitable zone. It's 250 million years for Jupiter, and this is longer than our upper limits for the origin of life on Earth, but it might be longer than the lower limits. But we also have to remember that we have many different, we have many of these outer worlds that are going to be habitable separately in the same system. So in order for us to evaluate the probability that life forms on any one of these outer worlds in a specific stellar system, we first want to calculate the probability that life doesn't form on any one of them, and we'll just take the complement, 1 minus. Okay, so here I'm going to walk through the math quite quick. We consider some random variable y to be the number of times life forms on any one of the outer worlds of a stellar system. And this is going to be the product of the independent probabilities that life forms on any one of those. And each of these individual probabilities can be modeled by a Poisson distribution. And we're going to assume that the probability here scales with the surface area of the world, which is sort of indicative of having the origin of life scenarios either at the surface of the planet in sort of shallow ponds, or as a sort of first order approximation to these hydrothermal vents, in saying that a bigger world should also have a bigger surface area for near the bottom of the ocean. And so the argument is that more sites for life to form should favor the formation of life happening quicker if it's just a random event. Okay, so what's plotted here is basically this function, and importantly, we don't assume a value for this average time it takes for life to form in an Earth-sized world. We leave this up to interpretation. So this was, you can either take, I mean, some figure here, 200 million years, if you do Luca estimates, or you could say 1 billion years and be conservative, or you could say that Earth got very lucky and it should take way longer than it did on average. But what we can see if we plot this and just focus on the total probability plot, I guess, here is that even if you take this conservative upper limit for the average time for life to form on a habitable Earth-sized world, if we sum up all the probabilities of all the outer moons in the solar system And those are the ones I use. I don't use any areas of outer terrestrials because we don't know them, right? I can only use what we have in our solar system. But even so, it becomes 15%, which is quite significant, I think. But there's a huge caveat to this argument, which is the assumption that a world is habitable as long as it's inside the habitable zone, which is not a fact. This is just demonstrably false, which is sort of what this justifies. This justifies further study into what we expect in terms of atmospheres for these outer worlds, because this is what's going to determine the habitability of these outer worlds. I mean, whether they are inside the habitable zone or not just says that they can be habitable if they have the perfect atmosphere. Okay, conclusions though. We found this secondary time inside the habitable zone that is sometimes comparable or longer than the first time inside the habitable zone, which I thought was quite interesting. And this is going to be insensitive to whether you have a narrow or wide habitable zone limit or habitable zone range, because the horizontal branch luminosity is so nearly constant that it's always going to be these 100 million years to 120 million years that the duration of the horizontal branch is. We also found this water loss being insufficient to exclude any secondary times inside the habitable zone for any of our considered outer worlds. But then also in our comparison to the timetable of evolution on Earth, we find that this time spent inside the habitable zone is shorter than the upper limit, but some of them are actually longer than the lower limit based on this Luca dating. And the fact that it is this comparable order of magnitude, and also that we have a number of these outer worlds makes these outer worlds I guess it justifies their existence as candidates for habitability. And I think that's it for me.
Victor, we have time for some questions. Chris, do you have a question?
Yeah, I have two questions. One is, as the sun evolves on the red giant, it's going to lose a lot of mass, and so I would think the orbits of all the planets are going to expand outward. Is that something you want to consider in the future?
Yes, so the parsec tracks actually include the current mass of the sun, so you can do that. But prior to the AGB, the mass loss isn't big enough that the orbits are going to be perturbed for these outer worlds, which is why it's not included, because the time spent inside the habitable phases occur prior to this mass loss being significant.
And then just a second question. So the runaway greenhouse, it also depends on the gravity of the planet. Lower gravity makes it easier to run away. And so since your focus is on moons and things like that, yeah, that was just a thing I had in mind when thinking about how easy it is to run away in the future for your habitable zone limit.
Yeah, that's included in this water loss thing, right?
Yeah, that's included in the water loss thing.
Okay.
So yeah, this is the mass of the orbiting world. So even for this moon mass here, you can see that the water loss is still at most 5 Earth oceans, because so for the runaway greenhouse, the oceans all evaporate instantly in my view, and they end up only existing as water vapor, but the water vapor isn't lost to space instantly. That happens over some time scale. And how much you lose in this time scale is going to be mass dependent. Yes.
Actually, how good is this energy limited escape rate assumption? I would expect that the actual escape rate should be much smaller, because it's a kinetic process, and it's not all energy goes into the outflow, right? I mean, some of it will be obviously irradiated, so the actual mass loss probably is going to be way smaller than this.
Yeah, so this I first did the diffusion limited water loss, but then the referee correctly pointed out that we are going to be in the hydrodynamical regime, because we have essentially water atmosphere and that's it, because the entire Earth ocean mass existing in the atmosphere, that's going to dwarf out any other molecules or whatever. And this energy limited escape rate is a way of calculating this hydrodynamical regime of water loss. And again, it's an approximation, but based on the fact that this is as you say, if this overstates the water loss, and we conclude that even this is insufficient, then I don't need to move any further with more accurate calculations, I guess.
And just one comment, while you probably indeed don't need to include this mass loss because it's such a short lead moment in the life of the star. I mean, when the star has such a high luminosity and has so expanded, what you might get for the nearer planets, like Jupiter and so on, is actually the tidal in spiral of these planets towards a star, because a star is basically non-rotating. The planet is going to be raising the tidal bulge on it. And there have been calculations done of this process, that actually when the luminosity is highest, the planets are going to move inwards. And so that will boost up the insolation flux on them. So this might be a fact that you might want to consider.
Yeah, I did consider this. I can't remember the paper I looked into, but they were stating some ranges for how far away you have to be from the sun as it evolves through a giant branch to become perturbed by these tidal effects.
Several EU is where these effects would matter.
Yes. So, but for our timescales, it didn't appear to be too relevant, because these occurring in the red giant branch, they're near the. I mean, Jupiter occurs earlier in the red giant branch, the luminosity here, as compared to the later ones, and those are further out. But this tidal effect, I don't have the numbers on me, but I remember I checked it, and it didn't seem to affect it too much, the results.
Okay, sorry, we have to move on. You can put it in the chat. Both of you, because you have funny expression on your face, so put it in the chat. Argue with Roman about it in the break.
No, I didn't have any argument.
Okay, thank you so much, Viktor. I really appreciate it. I know it's late for you, so have a good night's sleep, and greetings to Anders when you see him at work tomorrow.
I will. Okay.
Bye-bye. Okay, Kevin, please take it away.
Just share my screen?
You may share your screen. Yes, sir.
There we go.
Yes, perfect. Thank you. So I should say that Vasuda was supposed to give this talk, but because of Mike's incompetence and the incompetence of the security staff, I could not get her in the building. So Kevin is going to give the talk on Vasuda's behalf. So thank you, Kevin.
Right, thank you. Yes, so so this work was done by my graduate student Vasuda, Trehan, me, and Michael Way. And we are basically working on the machine learning system that will be trained to predict atmospheric absorption spectra given our ensemble of planetary parameters. So this will be trained using atmospheric spectra from solar system data and from atmospheric spectra generated synthetically by GCM models. Basically, you can see up here, we have generate some synthetic atmospheric absorption spectra. These will be binned in some way to form histogram approximations to the spectrum. And then the machine learning system will be trained to know the bin heights of each of these spectral bins given the different planetary parameters. So here I've only shown two dimensions here, and this hypothetical sheet shows how each bin in the spectrum varies as a function of planetary parameter. By comparing these predictions to actual data, such a system would be able to compute likelihood functions in a Bayesian calculation, And so it would be useful in that way. And you could use this and performing inferences. So given recorded atmospheric absorption spectra and being able to make predictions based on planetary parameters by generating a likelihood function, you can then compute posterior probabilities and then compute the most probable model parameters for a given planet. Now, of course, here I'm showing this in 2 dimensions. We're really looking down the barrel of modeling about 30 planetary parameters. So this is a modeling problem in 30 dimensions, which is daunting. Right, so we plan to bin these approximately using about 24 bin or 20 bins. So each bin height is going to be a function of 30 planetary parameters, and then the idea is to use a machine learning system to figure out what these functions are. So this is, in some ways, this is a case of very sophisticated curve fitting. Now, we talked this morning actually about possibly not using uniform width bins, and so this binning may change. In our simulations for this project, we just considered 6 bins and looked at how this worked using a simple model. So for our first pass, we considered just 1 planetary parameter. We're doing this all synthetically, so it doesn't matter what that parameter is, we'll just call it X. The spectral bin heights, we're decided to model those using spline curves in 1 dimension. So we're basically for each bin in the spectral histogram, you are modeling that variation as a function of the planetary parameter using a spline. And so the model parameters consist of a certain number of spline knots. We used 6 spline knots here in this test, and only modeled 6 spectral bins to keep things simple so we could visually demonstrate what's going on. So here in the synthetic spectra, we had defined these functions. So we actually know what the functions are. We're going to see if we can recover them. And so this shows how the planetary parameter X changes and shows how these different bins will vary as a function of X. And the data that we're using to train on are basically these 6 illustrated very coarse-grained spectra at these values of X. So we used 6 spline knots to model each of these curves. 2 of the spline knots are fixed at X equals 0 and X equals 1, the extremes, so that we can control these are basically in a spline, you're modeling the regions in between these spline knots with a cubic function, and polynomials tend to go off to infinity. So we are, by keeping spline knots fixed at X equals 0 and X equals 1, we can manage these things blowing up in the region that we're interested in. They were also constrained to be no more than 0.1 distance away from each other. So these spline knots are going to be allowed to be, the 4 interior spline knots are going to be allowed to vary in the X direction and in the Y direction, so we can model these curves. And we used a Gaussian log likelihood with a set sigma just to try this out, and we used the nested sampling algorithm to do the optimization. So here are the results using these 6 pieces of data. These light circles, which are hard to see here, and these vertical lines are where the data points were. And of course, those are going to match the spline curve very well. The mean fit is given by this blue dashed line. You can see it's rather uncontrolled where we don't have data, not surprisingly. And this is how it varies for each of the 6 bins. The sum of the squared residuals across the bins is demonstrated down or illustrated down here in subpanel G. And these are the sum of the squared residuals, and the the optimization algorithm actually keeps a population of the posterior distribution, so we can compute both the mean and the variance of that distribution. And the variance is illustrated by the colored width of these curves on these plots. So you can see there's a lot of variation in the possible solutions in the places where we don't have data. And that's illustrated, basically summed up here literally, to create the sum of the squared deviations over the bins. Now, what we did then is we employed the ideas of Bayesian adaptive exploration, where the amount of potential information you can get from taking a new measurement is going to be dependent or proportional on the amount of information in that distribution or the entropy of that distribution. Since we're using Gaussian probabilities for the likelihoods, the posteriors are basically Gaussian, and the entropy of a Gaussian is proportional to the variance. So looking at the regions where you have the largest variance in the posterior probability, those are the places where it would be best to collect data. And so these are going to correspond to these peaks here. So here at a 0.15, at a 0.5151, and around 8.5 are the best places to collect more data. So now not only do we actually perform this fitting and optimization, we can figure out where we need to collect more samples to do better, which is one of the big problems that we face. So here we're going to look at the one where the standard deviation is the highest, or the variance is the highest at 0.85. And so the next screen will show what happens if we add a spectrum at that X position. And so introducing another data spectrum, so now we've got 7 of them. One of them is at 0.85. You can see the variations dropped dramatically here in each of the bins because we now have a data point there. And it's actually controlled some of the variance elsewhere as well. And so the fit's greatly improved. This is the sum of the squared residuals. I'll go back to where it was. That was what it was before, and now it's shifted a bit. So you can see the lower end is now less certain because we've collected a lot more data up here. And the sum of the squared deviations now show that we've had very little variance in the large values of parameter X. So now this still suggests that we should probably collect some data at X equals 0.5 and X equals 0.15. And on the next screen, we do that and show that these curves are very well fit now. So we've got excellent fits. And you can see this from the sum of the squared residuals has dropped dramatically. The maxima are here at the extremes and are another order of magnitude less than from what they were before. So we brought the errors down by an order of magnitude by collecting those 3 data points in the places that the variance indicated. And of course, you can continue this game if you need to. You probably would be a good idea to collect some data here at X equals 0, or here around 0.25. And that would bring the residuals down further. So basically, this problem is a curve fitting problem. So in some sense, we understand it well. The difficulty is that we have to do this in 30 dimensions, and that's daunting. A spline model is not going to scale well. And so now we're looking at using Gaussian processes instead of splines to fit these curves. But the application Bayesian adaptive exploration by collecting new samples wherever the variance was high was very effective. And that is basically it.
Okay, great. Thank you, Evan. We have a schedule.
Yeah, thank you. You're welcome.
Any questions?
Are we gonna start having team meetings to design the actual ensemble?
Well, we've been discussing this separately from that for now, because we're trying to get the algorithm straight.
Right, but when should we start having
team input.
Well, I have to get this working first, and then we'll move on to deciding that stuff. But we're having those discussions as well. So.
Okay, I just had to raise a question about the idea in the proposal of the interpolating between Spectra, because you can get planets that are very, very similar, but just some things different, slightly different, and they're totally different. They're not going to have similar spectra and get interpolated between them.
Right.
So, yeah.
Well, like you said, it's a daunting problem.
Yeah.
But I think one thing that I think you were kind of showing here, Kevin, was that if you go back a few slides, I mean, he's basically his data points come from the bin spectra. And I think what this is showing is, at least for that particular spectrum, if you change the binning a small amount, basically you sample in areas where you don't have a lot of, where you have more information, you can make this work much better. So in a sense, that will tell us how much we can bin the data up, in a sense.
Waiting. Yeah. So you're waiting. You're waiting then.
You were deciding how to bin the data up.
Yeah. Okay, but you're saying.
Yeah, you could include the binning parameters as a model parameter and look at the variances that you get in those dimensions. And then that'll tell you how better to bin the data. So you can use this to bin the data better as well.
Right, because we can't use the full planetary spectrum, right? That's the point here. It's too high dimension. So this is a dimensionality reduction issue. So how drastically can we reduce the dimension but still have enough information to categorize data in the sense of what we're talking about?
And so to get that, you have to model these probability distributions, because the entropy of those distributions will tell you where the information is. Because entropy is proportional to information. So
yeah.
Other questions?
Yeah, I wanted to point out a few things about the details of the habitable world spectral range and resolution. First, it's almost certain we're not going to go past 2 microns and probably not past 1.7 microns for the coronography for hab worlds. So that could change. Just keep that in mind, and probably going down all the way to 0.25, which it looks like you already go down to, but the near UV. And the other factor is that you only will essentially get a 20% bandpass in a single observation. And then you'll have to revisit again to get another 20% bandpass. So 20% as in, plus or minus 10% around essential wavelength. So you would probably have a very different type of sort of spectral dimensionality, as Mike called it, essentially, for a single observation. And that may change how efficient you could be. Just something to keep in mind. I'm happy to provide more detailed information offline on that.
Great, Avi. How certain are they about this wavelength range for HWO, though? It's so far away, it seems. Are they going to decide detectors in the next 5 years for something that won't fly for 25 years?
It's not so much about the detector, but about the temperature of the telescope. Because if you have a room temperature telescope, as in a giant, flight bay testing chamber that you probably want to keep at a normal room temperature, that's where you want to test everything. You need your telescope to fly at that same temperature. So if you have a room temperature telescope, your thermal background starts to rise precipitously between 1.7 and 1.8 microns. So if they want to go beyond that significantly, they have to cool the telescope, by 10s, 20s, 30s of degrees. It starts to become much more complicated. And so you have to have a strong motivation to go past 1.8 microns. And you can see here that the signal that you're getting from your planet drops as well. And the ability to constrain specific spectral features becomes duplicative, primarily beyond 1.8 microns. You have CO, CO2, methane absorption features shortwards of 1.8 microns. So it certainly isn't decided now. There's always going to be, pushback and discussion, but I would see that it doesn't go beyond 2 microns and probably shorter than that. Just my guess.
So you're saying that they're definitely not going to have a big shield like JWST does.
They're going to have a shield, but not a thermal shield. It would be
okay.
Or,
so they're not going to build something that complicated again. They learned their lesson. Is that what you're saying? Is that you think they really learned their lesson? I don't know.
I think they've learned well, we as scientists have not learned our lesson, but the engineers certainly learned a lot of hard lessons.
But in 25 years, those people will be dead.
They got to make those big decisions about things like the thermal environment of the telescope, soon, in the next few years, so they can really move forward past that. And so they're trying.
That's what I'm wondering. That's what I'm really confused by, because I don't. Maybe you have better insight into this, but I don't. I mean, since this is all kind of new, and they only got started since the decadal finished. It's like, when are these decisions going to be made, or when do they have to be made given a certain launch date? Has that really been discussed at all? I mean, what are they doing?
They have 3 different exploratory analytic concept architectures that they are using now to pin down things like what's the thermal design, what's the optical path, what's the packaging of one instrument versus another, basically based on the design of the primary mirror. So yeah, they are really digging into those specific questions, because the goal is by the end of this decade to essentially have a single design that goes into mission concept review, MCR, and can sort of nail down all those unknowns. So yeah, the answer is yes. They are really working very hard to.
Good, I didn't know about that. That's encouraging.
And actually, now something occurs to me in this discussion is that because we have spectra, because you've already generated spectra from so many different kinds of planets, looking at that distribution, the probability distribution of the spectral amplitudes as a function of wavelength, the entropy of that distribution as you vary wavelength should tell you where the most information is about differentiating planets from each other. And that would tell you which wavelengths you would want to be measuring.
Right, but except he told us that basically they're never going to go beyond 2 microns.
That's right, but it might be good to know if you would want to measure something below 2 microns or something.
Don't tell them about that.
But I'm saying that's something we could actually study right now.
Yeah.
Given the data that you already have.
Yeah.
And I saw that Jen, hello Jen, you had your hand up, I think.
Well, did you?
Hi, yeah. A couple of clarifying questions. When you say nested sampling, is this straight nested sampling, multi-nest, or one of the other versions out there? Mostly out of curiosity.
Oh, it was just vanilla nested sampling.
Okay, yeah.
I literally took the original algorithm and just modified, just threw in our problem.
Yeah. No, that makes sense. You already answered my question about splines, because you'll recall some of the experiences I had with overfitting from using splines. I guess one of my other questions is like, so for parameter X, and we're exploring a space for parameter X, and you mentioned there are 30 planetary parameters, but when you're talking about the data is wavelength versus albedo, or as in this plot, is the data always like spectra of this type?
Yes. Yeah, as far as I'm sure.
Yeah, that's what I thought. So I imagine then if you're looking to probe different planetary parameters, the wavelengths of most interest in where you can collapse your function most readily is going to change. Like, there's probably more information about, for example, temperature in some wavelengths versus others, like naturally.
Yeah, certainly.
Um,
And that's something I was saying just a moment ago that we could explore by
Yeah.
looking at what's already been collected. You can look at it across different dimensions or all of it together and look at where the most information is.
You might even be able to set some priors that way too on expected data ranges and parameter spaces. Just
know, we're
anything
prob-
you can do to collapse the function.
Yeah.
Because 30 is a lot. Yeah. All right. Cool. Thank you.
Right, thank you, Jen.
Okay, are there questions? Okay, good. Well, I think we can move on then and get a little ahead.
Mike,
Yeah,
I have to go for a meeting at 4.
sure.
Are we doing dinner?
Yes, we are at 6.
6 o'clock downstairs?
We're going to go to Le Mans. We're going to be there at 6.
Okay, I'll meet you there.
Okay, perfect. Okay. Okay, Connor, I think, what's that?
Mostly like half joking, suggest that we could build a telescope and implement a shadow region on the moon. I don't know if anybody ever considered.
It's been discussed, yes.
Because then you have stable temperature actually.
If you put it in a permanently shadowed region, yeah, that's been discussed, but I think the biggest problem is the dust environment is very challenging. For example, that's one thing I've heard is the dust environment is very challenging.
Yeah, I guess it should be correct. I mean, it's coming from the people who are working there. It's not like it's coming
Well,
from the moon.
or any nearby impaction.
I don't.
Okay, anyway, this is, we can discuss this another time, like, sure, this has been discussed
5 minutes.
many times. Also putting a radio telescope on the far side of the moon is like the quietest place in the solar system, but it's very expensive.
Yeah, but if they've got sun there.
No, for radio, it doesn't matter. For optical, you don't want the sun hitting your telescope. Definitely. Okay, Connor, go ahead. Why don't you take it away?
All right. We'll share my screen.
Yep.
I'm in some little box here at the University of Michigan. So let me know if the connectivity goes out. Hopefully it stays good.
Okay, we'll let you know. Hopefully you can hear us.
I can. Am I sharing my
when it
screen?
cuts out.
Can you guys see this?
I can see it in presenter mode.
Okay. How does
There
that
you go.
look?
Perfect.
All right. Let me just move this little bar out of the way. All right, well, this has been a great meeting so far. Thanks, Mike, for asking me to join. So I'm Connor, now a graduate student at University of Michigan, as I mentioned. And I'm going to talk about some work. Many of you may remember some of this, hopefully. It'll have some updates, significant updates, and it's on spectral detectability simulations with ROCKE-3D and PSG. And I'm also going to be talking about some HWO observables specifically about surface biosignatures, but hopefully go a little broader as well. So thanks to my co-authors listed here. As I mentioned, I'm an MIT student. I started this work as an undergrad at Columbia. The rest of my collaborators are at other NASA centers. And thanks to you, those of you at GIST who've helped out, and several folks at Goddard who've been a big help as well. They're not listed here. But let's jump into it if I can see how to, there you go. Okay, so this work is kind of a nice use case, basically for ROCKE-3D. So we have a paper out on arXiv now. It's accepted to PSJ. We're just working on the proofs right now. And so I'll give an overview of all the updates that we've made, significant overhauls, and some HWO observables and applications. As many of you know, I'm sure we're in the working groups are fired up, and we're trying to get the science traceability matrix for whatever we want to observe. Specifically, I'm working on the surface biosignatures working group, and so hopefully this work can be useful for applications like that. But I'm also going to be focusing on methods here that we use, which are quite general and can be used for any kind of detectability study that you want to do, whether it's a gaseous species or surface, whatever. And studies like that are very valuable and needed in the working groups. So. Yeah, I'll skip most of this background on Proximus NB, but I will say that we kind of use it as a limiting case because it's the closest exoplanet to us. It may be the best case for biosignature detection, just considering the inverse square law, brightness drop off. So we kind of use it a limit like that. Because before embarking on this work, we didn't really know if surface biosignatures were going to be detectable at all on any exoplanet, much less the further away ones. And we show that it should be detectable on nearby exoplanets, even further than Proxima, actually. But as Avi kind of mentioned, I was going to mention that at the end, but with the current HWO coronagraph specifications, Proxima may not be accessible because it's too close to the parent star. Here we use the parameters of Mdwarf, so it is accessible with that coronagraph. But in general, this work does serve as a kind of a still getting at the detectability of biosignatures. Now we just need to do it for like FGK stars and other habitable environments. So I'll talk more about that at the end, kind of showing why this work is still relevant. So yeah, it's a biosignature detectability study using ROCKE-3D states and PSG as a radiative transfer model. These images here at the left are one of the Proxima B climate states from the Del Genio et al. 19 paper. Control is the name of it. The top left is basically the state from the paper straight out of the box. So it appears orange because Proxima is a very cool star, so emits mostly red light. This horseshoe shape is the water clouds there. You can see in the plot at the right, that's a cloud cover fraction. I'll back up for a second. This dark part is the ocean. The rest of the surface is ice. And then Earth-like atmospheres with various greenhouse gases. And then the bottom right here is false color image of this planet with a bacteria-like organism which strongly absorbs at 1 micron. And that's the biosignature that we go after because it's well adapted for Proxima. If you place the RGB channels such as indicated here, you get this is how the planet looks. This is a real radiative transfer. It's done with PSG. So it would look invisible with the bacteria added. And I generated these with codes from Vincent Kaufman, and now they're up on the NASA PSG GitHub. If you want to create images like these, it's pretty easy to port over to ROCKE-3D. I think they're developed for MERA, but it's pretty easy to port over. Hopefully, maybe I'll talk about this tomorrow in his talk with Hima. So it's a cool way to check out how GCM states look. So as I mentioned, this is the biosignature feature that we go after. I'll kind of speed through this. Many of you might remember this. This is the Blastochlorus viridis spectrum, which is a purple bacteria in Anastophototroph that one of our co-authors measured in her lab. It absorbs strongly right there at 1 micron, so it's using this near-infrared light for photosynthesis. The red curve is the photon flux density availability at the surface of this Proximus NB state. And you can see there's a large availability of photons right there at 1 micron, kind of bounded on either side by water absorbance features. And so this could be a good thing that could live on such a planet. And the spectrum that we actually use for biosignature detectability is this black line here. It's a we scaled up the contrast of this QY feature. That the QY is the 1 micron absorbance feature, this little dip there. So we wanted to scale up the contrast. And by contrast, I mean the peak minus the trough, so that the contrast is similar to the vegetation red edge. And we've taken the VRE to be the highest contrast spectral feature possible. It's kind of another limit of life on Earth. And we wanted to simulate like a maximum cell density. And so that's our initial spectrum, and then we scale it down. We dilute it linearly to test like kind of how much of this stuff do you have to put on the planet for it to be detectable. That's the question we want to answer. Like, what abundance of bacteria do you need to be detectable? And so that dilution factor will essentially give you your answer. Where this is the like a pure surface of this would be 100% covered. So hopefully that illustrates why we scaled it up. So microbes in situ generally don't reach this high of spectral contrast. So we call it a Beaveridis-like organism, or BVLO. You know, contrasts like this are super high cell densities, or something like land plants. I'll discuss that more later, like what kind of feature this may represent if it's a super high contrast. So like I said, we took the Proximus NB states from Del Genio et al. 2019, added the surface biosignatures to them in post. We chose, considering that Earth is an exoplanet strategy, a search strategy, we chose to simulate spectra from some Proterozoic-like states, which is a control state. There's a clear sky and anoxic atmosphere. That's why I call it kind of Proterozoic-like. And notably, biosignatures are kind of absent from Proterozoic-like states. We had this equilibrium, atmosphere stuff, but that's pretty new work. But surface biosignatures would be a nice companion to have to these, where kind of atmospheric signatures are less obvious. And then we chose some Archean-like analogs. I should say no directly observed atmospheric signatures. The indirectly ones possibly, like I said. And then we chose the Archean states from that paper with high methane and possibly hazy atmospheres. We added the hazes in the post because they weren't simulated in the GCM. We took the hazes from Meadows et al. 2018. And considering some of the parameter space that hazes form, we think they would probably form on these planets, but they maybe wouldn't. We put them in uniformly over the globe, but this may not be a great assumption. I think Eric will talk more about this in his talk on day 3. So looking forward to that. And so all of these GCM states have a large degree of ice coverage and a good amount of open water to the surface, making them habitable in kind of lobster pattern near the substellar point. So this is how we put the organism or the surface biosignature onto the surface of the planet. It's a very simple equation. So this gives you the surface area coverage fraction of the organism, or the dilution factor from that scaled up spectra. This is a kind of scalar across the planet to dilute the whole thing. I'll talk about about that later. These all range from 0 to 1. This is the open water fraction. This equation is solved at every grid cell. So this is the open water fraction. This is a function of temperature, which I give down here, specifically the sea surface temperature. We assume that this BVLO is well adapted to live on cold planets, and then we have a function of photosynthetically active radiation, so it grows better with more light, and you know, some optimum temperature. So that gives you the abundance of the bacteria, the surface area coverage fraction. Ideally, the biology would be prognostically simulated at runtime, but we didn't have that in these GCMs. So you could use something like the ocean biogeochemistry simulations that Natas is doing there at GISS, and track the nutrient parameters like silicon and other nutrients. That'd be a really interesting next step to kind of parameterize the organismal abundance, and you could do vegetation studies and things like that and test the detectability of that. So like I said, these are straight out of GCM. Basically, state you you get these arrays, and then you scale them up and down by this A max parameter that varies from 0 to 1. And so that's how you test your what abundance is kind of detectable. And it gives you the surface area coverage fraction at each grid cell. And yeah, with simulating at runtime, what would be interesting to do is some kind of time variance in these abundances, and see if that time variation is detectable. I think that would be a very interesting next study to actually go through and calculate the integration times for the time variation. That might lend support to it being some kind of biological activity. So interesting ideas for future work. So there are those basically coverage fraction maps. And it's just showing that this is how much bacteria there is in each longitude band. And so you put these maps onto the surface, the state in post using PSG. And so a quick word about how PSG models the surfaces. It uses a linear areal mixing principle. So each surface component's reflectance spectrum, that's here, R sub I and lambda. The reflectance spectrum is weighted by its cover fraction, which I denote by AI. And so it's all the reflectance spectra are linearly mixed together. And so therefore, to give you the reflectance spectrum of the surface, so this coverage fraction of the bacteria-like organism is really a spectral dilution factor. I think it's a more physical way to think about it. So we want to know basically how much spectral contrast this sort of biosignature have to be detectable. So albedo maps of a planetary surface could in theory be retrieved by future telescope observatories and possibly HWO using a method proposed by Berg-Ugina and Kuhn in 2019. So you could map out the surface, and you could essentially, in theory, use this method to retrieve a map of this QY feature of this map that I'm showing here, but it could require very long integration times. And retrievals of surface albedo like this might be complicated for tidally locked planets as they enter the inner working angle and get blocked by the coronagraph, but interesting to think about that might be detectable. So I'll speed through this. PSG is the radio transfer model that we use. You can adjust the GCM state and generate observations. I'm sure Thomas and Vincent will talk more about that tomorrow. You can define what observatory you want to use to synthesize the spectrum. We use LUVOIR A and B, and LUVOIR B is 8 meters. And so it's kind of a proxy for HWO. The parameters are still being defined. They weren't really well defined, less well defined than they are now when we started this. But we're using LUVOIR B as a proxy for HWO and trying to infer what might be detectable in that way. So this is a spectrum that we generate for the control state as observed with LUVOIR B. And the purple line is the planet with the BVLO with the QI feature present. And the black line is the planet without the QI feature present. And so you can see that this bacteria species is decreasing the planetary albedo in this band here. And the orange is the simulated noise. And so this kind of forward modeling allows you to know exactly how much impact the biosignature will make on the planetary reflection spectrum. And this is what we want to detect. Like this difference here is kind of what we're going after. We want it to be below the noise. And so this little increase in noise that you see transitioning after 1 micron is a transition from using a CCD to a mercury cadmium solarium detector in the near infrared. So just taking into account some considerations like that will have to be taken into account when you're making decisions about what you want to observe with HWO. So I'll note quickly here that, different species in the atmosphere or the surface could absorb also at this same wavelength, and it could confuse you. Are you seeing absorbance from methane, for example, absorbs right there at 1 micron? Or is this the surface biosignature feature? So it's a complex problem, and large efforts are currently undergoing in the working groups for HWO. And I'll touch on that again here. Basically, we add more methane to the planet to try to mimic the feature. But what we find is that when you add more methane to the planet, this blue line, you start to get way more absorption at other wavelengths. And so what you can do, if you know that a gaseous species or some known absorber also absorbs at this wavelength, where you see some unknown blip, you can also observe at that other wavelength. So for methane, it's right here, and you just observe there, and that's how you'd be able to determine that it's methane or some other known absorber in the spectral library, if you see also an increase in absorbance there. So it highlights the need for multi-wavelength observations. You probably could not get this in very large, even with a very large bandpass. But yeah, some kind of technology to and repeated observations at different wavelengths. So also interesting thing to discuss as far as observables. For these Archean high scenario, with the high meaning a lots of methane, it was much more cloudy on the Eastern Hemisphere, which the Eastern Hemisphere is in view at a phase of 270 as the planet orbits around. We observe at quadrature at 90 degrees and 270, completely on the opposite side. So it's much more cloudy on the eastern half, and so the planetary albedo is much higher when you observe at that phase. And so this is visible as a higher continuum, spectral continuum. And so you could observe something like this in a phase curve if you observed at as the planet goes around. So there is however, you probably couldn't really infer if it's a higher surface albedo or a higher albedo, planetary albedo, due to something like a cloud deck, as it is here. And planetary albedo is also degenerate with planetary radius, but that radius obviously wouldn't change as you do a phase curve. So you could do a phase curve and constrain the longitudinal differences in planetary albedo. We find that for surface biosignatures, more clouds increase the integration time because they transmit less light to the surface. But interestingly, for well-mixed species that are well-mixed well into the stratosphere, clouds actually decrease the integration time because of the higher planetary albedo. So you get more light interacting with your species. And that's from work from Kelkar, and I think Ravi and some others from Goddard were on that. I'm not sure if it's published yet, but that was interesting. The discussion of clouds and how that might affect detectability. So yeah, you use the synthetic spectra to calculate detectability in this way. You just take the difference of your curves here and then divide by the noise, and that gives you the signal noise ratio at each wavelength. And you use this, you basically scale your SNR linearly by some known initial integration time. And you can use this method to detect any detectability of any component you want, basically on the planet, with this kind of forward modeling. And using ROCKE-3D is a just very nice, rigorous way to model the planet and make sure you get this kind of signal exactly right. And basically, because it's a very sensitive function, the detectability, so details are quite important there. And so this is the integration times that we calculate for various dilution factors or various area coverage fractions. And so this is the x-axis here. Essentially, this number here is the surface area coverage fraction, or the covering 13% there would be this number, or that initial scaled up spectrum has been 13% diluted and it covers the whole planet. So that's how you can think about this number here. And then on the y-axis is just the integration time to achieve a signal noise ratio of 5. So I'll note also that future work is needed to determine what spectral dilution factors are realistic for what organisms and what organismal type. what kind of spectral strengths we can detect from or expect from alien organisms is an interesting area of future research, and we should compare it to terrestrial life as best as we can. So here, this dashed line is 1,000 hours of integration time, which we propose as is kind of a theoretical limit for how much telescope time you could possibly get for a single target. And so I use that as a threshold for detectability. So for this example, for control with LUVOIR V, you need LUVOIR B. You would need at least 1.5% of that initial spectral strength to be detectable, or 1.5% area coverage fraction, which is quite low. So for moderate area coverage fractions, your integration time is something like some tens of hours in general. So you need this number here to be 0.25 to get back to the original spectrum, and you need to dilute it a further, that scaled up spectrum, you need to dilute it a further 1 or 2 orders of magnitude to match the contrast of in situ microbes. And so what all that means is basically that real microbes and their spectral contrast will kind of live in this region here. So they're right at the edge of what could be detectable with HWO. So to be detectable, the organismal type or the spectral contrast that we get from it needs to be something larger. And this regime over here is something like what we have from land plants on Earth, like trees and grasses and all that, cover about 13–14% of the Earth, I think. Something on that order. And then we have something in the middle here, might be something like planet-wide bacterial mats, giving you a large contrast like that. So those kinds of things may be detectable. It'll be interesting to see what other organismal types may be detectable. So sorry for the table here in this talk, but basically what I'm trying to say here is that when you add more methane, basically this thing gets harder to detect, of course, because it's in the same band and the transmission is lower. And then we also found when we added the hazes, those hazes that we added increased the integration time by 1.4%, factor of 1.4, right? Because the hazes are more opaque, and so it decreases the hemispheric transmissivity. So it'll be interesting to simulate differences in hazes in the future. And also see how those are detectable, how they impede surface biosignature detectability, excuse me. So yeah, then we tested, so right, it may be detectable on Proxima b, but what about the further out planets? And we put the control state around a sun-like star, and we set it the semi-major axis to be 1 AU, otherwise it gets covered over by the coronagraph at this inner working angle. And so we're trying to solve that problem. Basically, we put it at 5, 10, and 15 parsecs, and we find that this surface biosignature becomes undetectable by 15 parsecs. But it should be detectable within that distance. And these results compare well with Borges et al. 2024, which was just released a couple months ago, and it compares very well with our results here, and that's very encouraging. And we're all going to be working together to try to do some future work and do some more of these calculational studies. So, right.
3 more minutes.
How many? 5?
3 minutes.
3, okay. I'll speed up real quick. So you really got to tie this to a target star list, which we didn't do, and which stars are in the solar neighborhood. So the HWO instruments may change. They're currently in development. Like I said about the inner working angle, Proxima may not be accessible, but this work kind of shows that surface biosignatures are worth going after. So however, probably look at them around FGK stars. We're talking about HWO. A large bandpass is desirable to observe these surface biosignatures, and you're going to want some way to stabilize your telescope to repeat observations. So the QY should be detectable in some tens of hours, very approximately, if it's present in enough abundance. service biosignature signature good to go after. We're going to be looking at this in a wider parameter space, different optical configurations in the working groups, and this kind of methodology with ROCKE-3D and PSG can be applied to a lot of different scenarios. And that's all I have. Thank you all.
Okay, time for a couple questions. Any questions for folks? Nice work, Connor. Thank you so much.
Yeah, thank you.
Few years working on this, so.
Yeah.
Should get, I'm gonna try to get you in a talk arranged in the astronomy department at Michigan, because I think they should see this. So.
Yeah, thank you. That'd be great.
Should I go, Mike?
Yeah, go for it, Ravi. Yes.
Great talk, Connor. Exciting to see you've done a ton of different scenarios, and especially with the hazes, that's very impressive overall. And I definitely would encourage, if you can, to sort of do a full sort of retrieval scenario. There's lots of different applications now, both Goddard and elsewhere, that can help with that. Because I think getting at that differentiation between the 1 micron feature and other molecular bands would be good to explore.
Yeah.
Yeah, go ahead.
Yeah, I think that's the next step in that service biosignature working group, is that we're gonna work with Jake's group and do some retrievals and check out with a couple of different pigments and see what we can get. See how that goes.
Very cool. I did, of course, with my other hat on, my MIRECLE hat, wonder about variations in emissivity for surface biosignatures as the flip side of the coin of albedo is, would you see any variation in the mid-infrared for different types of surface biota, things like this? And maybe this is a question for Nancy or someone else. I don't know. I haven't seen this explored for thermal emission as much.
Yeah, that would be quite interesting. I know plants do weird things to like dump their heat and stuff like that, but I'm really not much of a actually pigment spectrum person. But maybe Nancy or Nikki or someone could elaborate on that. But yeah, that would be very interesting to explore that.
Sorry, I was typing something. What was your question, Avi?
In the mid-infrared for emission variations, if you're looking at the thermal emission of a planet and you have different surface biota, would you see differences, spectral differences that could be signatures of surface biosignatures?
I don't think the organism spectra tends to be only characterized out in the short wave. So for mid-infrared, where are you saying? I mean, you can see different chemical, like cellulose or lignin or other things that are not pigments in the spectrum. But yeah, I don't think most people have fielded spectrometers that don't go past 2,500 nanometers. So maybe this is something that we have to look at characterizing organisms a little bit broader spectrum.
Yeah, no, I guess I was thinking about some of the Earth observing, work that's being done looking at down with different mid-infrared spectrometers and examining different biological species, right? Haven't people done things like forests versus savannas and all different things in the mid-infrared? Could there be information that could be used for similar
Yeah, I don't think it's been investigated well.
Okay. Cool.
Okay, thank you, Connor. Let's move on to our final topic before the next break. And I asked Ravi Kopparapu to come and talk to us about 2 of the ICAR programs that he's involved with down at Goddard and in collaboration with APL, at least one of them, about characterizing habitable zone Mdwarf. So Ravi, you're there.
Yes, Sam.
Hooray! This is network collapsed at Goddard about an hour ago, so it's good to hear.
So we are on I was on a hotspot, but now I'm on a not a Wi-Fi, but a wired connection. So
Okay, perfect.
going to share my screen. Let me know if you can see it. Can you all see this one?
See it. See it in presenter mode. And now we see it in the right mode. So go for it, Ravi. Thank you.
All right. Thank you, Mike, and good to see you all. I wish I saw you or met you all in person. My favorite place in New York, of course, but maybe next time. So this talk is about an ICAR program that we were funded to work on. ICAR is Interdisciplinary Consortium for Astrobiology Research. These are the new NAI kind of programs, NASA Astrobiology Institute kind of programs that try to address some fundamental questions about astrobiology by collecting a team of people with varied and diverse expertise to address these science questions. And our particular ICAR was focused on Mdwarf planets and the potential for life on them. This is the second iteration of the ICAR that we have been awarded. The first one was called the Mdwarf Opportunity back in 2020, and it was awarded for 3 years. We reproposed last year, and we got it renewed again, and we renamed it as Strange New Worlds. And anyone who knows me knows that I'm a Star Trek fan, and hence the name of this ICAR proposal. This ICAR proposal is mainly to characterize nearby Mdwarf habitable zone planets. That's what Mike just mentioned. And the project PI is Kevin Stevenson from Johns Hopkins APL, and I'm the science PI. And we have about more than 30 team members and among 19 institutions. And some of you are probably in this call. Many of them are co-Is and collaborators. We have deliberately tilted the team towards a little bit more youngish kind of team members, because that's where we think we draw our energy from and ideas also from them, with some expertise also from senior people. These the primary question that we wanted to answer from this CHAMS ICAR program is, can Mdwarf planets support life? And if so, how do we best observe and characterize them? And to do that, we have developed 4 tasks. And these tasks address several aspects of Mdwarf habitability, starting from the formation of these planets around M stars, and also their atmospheres, photochemistry, their climate, the star-planet interactions, and also the exoplanet, the Mdwarf planet observations. And these 4 tasks are sometimes linked. Some of the tasks deliveries are delivered to the other tasks, and there is feedback from some tasks to other ones. If this sounds complex, it is complex because the process of Mdwarf habitability itself is a little bit different than what we know about our solar system and Earth. The idea here is also to tie them to observations, either for James Webb observations that will yield some constraints on the atmospheres of these planets, and also on the models that we use to study these Mdwarf planets. And also, we want to look in this new proposal how the ground-based observatories could be used to study some of the transiting or non-transiting planets. Some of you may know or probably attended the SEEK conference that we have organized this year back in April. And the theme was on understanding and characterizing non-transiting planets. And there is a focus now more and more on that particular kind of systems. So we wanted to balance in this program, CHAMS program, both the transiting planets through James Webb observations and also the non-transiting planets through other means. Even for ground-based telescopes are upcoming or planned, or missions under study like the MIRECLE mission that Ravi probably talked about in the earlier. So I'm going to give you some highlights from our team members. And so bear with me. I'm not an expert in every one of them here. I'm just going to recite their accomplishments. And also these are, when I asked them to provide slides, they kindly provided these slides. Some of these were nuggets, science nuggets that we sent to the headquarters. And so if you have any questions, I may be probably able to answer on the top level, but if you want a little bit more details, I will almost surely fail. But then I'd request you to contact our team members then. This is, so we could start with task 1. This is from a task 1 group, Matt Clement, who is at APL, and Elsa Quintana at Goddard. They were studying the planet formation, habitable zone planet formation around Mdwarf stars, and they have published 2 papers on this one. The main idea from their paper is that during the planet formation around M-dwarfs, the asteroid belts are ubiquitous. They can be formed quite a bit around these M stars. And however, the debris material around habitable zone planets can be cleared very quickly, which means that the late stage bombardment may not happen from nearby vicinity of these habitable zone planets. However, they also found that there is a significant amount of icy body material in the asteroid belt, equivalent asteroid belt region around M stars, from where the habitable zone planets could derive or accumulate bombardments, which could make them not desiccated as we thought before. Probably some of you may remember that planets around habitable zone planets around M-dwarfs appear to be desiccated because of the high luminosity pre-main sequence of the host stars. The host stars are very bright in the beginning of the formation of the system. And there are papers that propose that some of them may get desiccated or may accumulate a lot of oxygen atmospheres if they had accumulated water at later stages. Matt's and Elisa's papers comment that even if the debris material around these planets nearby debris material clears off, the asteroid belt may provide some source of icy bodies for the bombardment. So if you have a super Neptune or a super Earth or a mini Neptune in these systems beyond the asteroid belt, they may perturb some of these icy bodies in the asteroid belt and could provide material to have some kind of a water or some kind of volatile material on these planets. However, having these large bodies of Neptunes or mini Neptunes could also prevent formation of asteroid belts in these systems. So it's a double-edged sword. And only the observations from Roman and other missions could probably provide some insights into what kind of a distribution of planets of different sizes could be there around these M-dwarfs. So I would recommend to look at these 2 papers that Matt and Elisa published. Oops, I am trying to move beyond. Okay, there you go. So we move from task 1, planet formation, to task 2, which is the climate model and atmospheric modeling of M-dwarf planets, which is led by Jacob Hugmishra, Thomas Fauché, and Eric Wolf, the usual suspects. And so I think some of you are here. I think many of you are also involved in this samosa intercomparison project. This is a part of the cuisines initiative that Tom and Linda and Kostas have led, and there are several different aspects of these cuisines, and one of them is this samosa. Samosa is a sparse atmospheric model sampling analysis. It's an ongoing intermodal comparison for M-dwarf habitability. The idea here is that if you want to explore climate states of habitable planets in a parameter space, you might, using 3D climate models, it might need a lot of resources and time. And so there is this method called the quasi-Monte Carlo sampling, where you can choose a representative point in each parameter, in a parameter grid that can represent the grid itself, and then perform your sampling or perform your modeling in that on that sample from that grid, so that you could reduce the computational cost and also not expend as much resources as you can. And there is this paper that Jacob and all published, where they show the comparison of this method of selecting representative samples from a grid of parameter space between two different models, ExoCam, which is the 3D climate model. I'm sure everyone is familiar with it, and Exoplasm, which is a simpler 3D climate model that they compared with. I don't know if you can see this clearly on the screen. The preliminary results from these intercomparisons show that there is some agreement in the habitable and cold region parameter space towards the right side of these two plots between Exocam and Exoplasm. However, if you go to hot, warm planets where they are just transitioning to runaway climates, there is some disagreement, and they do not match with it. So if you have a model that you think would be benefited by adding that to the Samosa protocol, please contact Jacob or Thomas Fosche. I don't know if Thomas is online. And you could also do this intercomparison of different models. So the idea from the Samosa intercomparison is to see how you can select representative samples and explore only a few places in the parameter grid and not the whole parameter. Okay, that's great. However, if you take it to a little bit beyond that, if you want to take that to and do something else with it, this is where an interesting interpolation scheme comes up, which is it's something called the Kriging method. So when you are running these climate models, they're computationally expensive, right? So, and you cannot easily explore all these parameter spaces. And even if you choose representative grid points, like I mentioned before in the previous slide, there are some empty spaces between two grid points that you may want to explore. I know you have explored into, you explored in different parameter spaces that may have be a representative of the grid itself, but there may be intermediate points between the grid points that you may want to explore for whatever reason, variety of reasons. And this is where you could interpolate between the 2 points and see how your method would be benefited from a particular scheme. Jacob found this method called Kriging. Apparently, it was used in mining ores in South Africa, and it was used in geospatial statistical analysis. And there were also some literature on using a Kriging method for climate models. And Jacob, Eric, and Thomas have developed this method for exoplanet GCM models and applied that to the same sparse sample model that we discussed before. And I truly encourage you to go through that paper. It's really good how this can be used. So if you have two data points and you want to get a data point in between and want to understand the climate state of a planet in that intermediate data point, you can use this Kriging method. And the plot on the left-hand side shows the sparse sample that they have selected, and the right-hand side shows the application of Kriging on that sparse sample, where you can then the color contour represents what the climate state could be. When I say the climate state, it's the temperature of the planet. That's the color scale that you are seeing. How the climate state could be between those open circles for using Kriging method. This is a very powerful method. There are limitations, of course. You can also use this Kriging method for observations as well. And so we have applied this only for the climate modeling of GCM models. if you are interested in applying this to any of your domain, please contact Jacob or Eric or Thoma. Okay. From task 2, we move on to task 3, which is where we perform star-planet interactions, photochemistry, and such. So this is work done by Michael Leong. She's a grad student at University of California, Riverside, with Eddie Schwetterman. Eddie and Thoma have collaborated with Michaela here. The idea here is to identify novel exoplanet biosignatures. One of them is a methyl bromide. They've also discussed another biosignature here, methyl chloride, in a previous paper. And their idea here is that to see if methyl bromide could potentially be detected in the atmospheres of Earth-like planets orbiting M stars. And why methyl bromide, and why methylation of these kind of chemicals? Why do we want to observe these kind of biosignatures? From what I understood, there can be false positive biosignatures in a variety of environmental conditions on exoplanets. And nature is clever, and so you could get some false positives even if you think that there is a combination of biochemicals that may point to a signature of life. Their idea here is that even though these chemicals may be a little bit low in abundance, they may provide a less avenue for false positive identification than other traditional biosignatures, gases that we are familiar with. And so they explored this particular one by methyl bromide, and they found that it is very active chemical in the mid-infrared parts of the spectrum, and hence Mdwarf planets are very conducive for this identification of this molecule. For one of the important things that they point out is that just like no single biosignature gas is a telltale sign of a confirmed sign of a life or a bisignature, methyl bromide itself may not be detectable, or maybe not itself without context is not a biosignature. However, if you have several methyl molecules in addition to traditional biosignature molecules, you can have co-additive effects that could increase the detectability of these gases within the mid-infrared spectrum. That could make it more robust detection of life on exoplanets around M-dwarf stars. So I like Eddie's work really well because he has these novel ideas, and I was very excited to see this paper. These gases are not produced in thermochemical equilibrium, and they are produced only in the disequilibrium processes that are possible during only when life is available on the planets. And so there's less chance for false positives of these kind of chemicals. All right, let's see. Oops, not going there. All right, this is another task 3 paper that Howard Chen, who is a faculty now at Florida Institute of Technology. Howard is we collaborated with the Gongji Lee, Georgia Tech, and they were studying what would be the effect of non-synchronicity in M-dwarf systems, planets in M-dwarf systems, on the climate states of those planets. Typically, we all assume, and even in our climate model simulations, we assume synchronous rotation of exoplanets. And so we want to make sure that, even in our climate GCM models, we assume and we implement 1:1 spin orbit resonance. Essentially, they are the same side of the planet is facing towards the star. And Howard and Gongji, they tried to couple an N-body spin orbit integrator along with Howard's GCM model to see what if you have perturbations, if you have multi-planet system, and if you have perturbations from the companion planets, they may kick the planets from 1:1 spin orbit resonant and put them into semi multiple resonance states, or in spin orbit variant states. And so if you have a non-resonant cases around on a planet around M star, how would it affect the climate and dynamics of these planets? And the conclusion here is that they did this experiment for TRAPPIST-1e and then 1f. And for at least the planets at the outer edge of the habitable zone, they are very vulnerable to rapid global glaciations to the point that they may not be able to come back from that glaciated state. And you see on the right-hand side here, the blue shaded region slowly disappears as the simulation time progresses from year 1, year 100, year 140 to year 170, and it becomes an ice, 0% ice free by the time the simulation ends, because they are in non-1:1 spin orbit resonant state because of the perturbations from the companion planets. All right. So, and then this is another model, stellar evolutionary model that Sarah Peacock, Michaela, and Eddie have worked on. They were trying to see how would the Lyman alpha profiles or Lyman alphas, the flux that we use from our stellar spectral models. There is this stellar spectral model, Phoenix model, that we use in our climate models and also in our photochemistry models, because we wanted to, so that we can use it in our radiative transfer calculations. And we also use the Lyman alpha line core flux value from these models. And Sarah tried to estimate what would be the effect of accurately modeling that particular Lyman alpha on the spectra of Mdwarf planets. And the conclusion here is that, as you can see, if we do underpredict the Lyman alpha flux from these stellar evolutionary models, apparently does not impact the modeling of Earth-like planet spectra to an extent. And this might have implications for photochemistry modeling. I have to talk to Sarah and see, is it a spectral, Mdwarf spectral dependent? Mdwarf have subspectral classes from M0 to M8, and they have, when we go from M0 to M8, they have a wide variety of luminosity and SED variation, SED, spectral energy distribution, how the Mdwarf spectra varies. So it is, we were going to explore how the SED variation from M0 to M8 would affect this particular result. And I think we have someone working on this as we speak. This is again another postdoc in our group, Laura Emerald. We're working with Evgenia Shkolnik at ASU. They tried to look at the atmospheric loss of terrestrial planets in the habitable zone. They use particularly they used it for some varying radii planets around a particular given stellar host star of 0.6 solar masses or so, and observe what happens if you have a quiescent star and a quiescent plus flaring star. And here on the x-axis, you will see the age of the star, and the y-axis, how much atmospheric mass has been lost. And as you can see, the red line is for a 1.3 Earth radii planet, and the flaring affects, or even if the planet is in the quiescent state, it affects the 1.3 Earth radii planet more than the 1.6 Earth radii planet. And it becomes even more disastrous if you include the flaring, even if it is not in the quiescent, if it include flaring. The red dashed line and the red solid curve that you see at the left side of the plot is showing how precipitously the atmospheric loss happens for this particular planet. And this paper is still, I guess, in preparation. Yes, it is in preparation. This is an exciting project as well. Marianne Limbach from University of Wisconsin, Kevin and Jake are leading to find planets around white dwarf stars. And we do know that the first exoplanet ever discovered was around a pulsar. And so they are trying to find the same similar planets around white dwarf stars using a method called PI, the planetary infrared access. If you model the star spectra perfectly, you could try to remove that spectra of the star from your data and then just see how the infrared excess, the infrared emission from the planet itself could be detected. And this works really well for white dwarf stars because white dwarf stars have a peak emission in the blue region of the spectrum, whereas planets have peak emission in the infrared part of the spectrum. So there is not much star contamination coming from the white dwarf stars. So you could potentially look for planets using this infrared excess method. And they have a James Webb program on this one for now. This is another use of pi technique from Laura Mayorga, also another postdoc working with Jake, Lustig, Egan, and Kevin. They wanted to see how multi-planet systems could be detected using the pi technique, and they applied it for TRAPPIST-1. And the result here is that for non-transiting planets, using pi, you can find planets that are present and measure their equilibrium temperatures. But you need to know the semi-major axis constraints that are very critical to this. I'm almost at the end of my talk. I know I have only a few more minutes. Two quick slides. This is our observers team. Many of them are from Penn State originated. They are the radial velocity observers. They are the ones who provide us with the planet detections of radial velocity discovered planets using their instrument, NUID instrument that is now installed on WIN 3.5 meter telescope. And they have they're working on a planet discovery, and that you may be hearing soon. We have a couple of other planets that we have obtained from them, and we worked and modeled these planets, all of them around Mdwarf stars. There are some upcoming and ongoing projects. Some of these people are here online. I think Anmol Desai, who is a new post-back in our group, is working on modeling thermal emission spectra of nearby habitable zone terrestrial planets using Exocam and PSG, and to assess these observability of these spectra with MIRECLE telescope. Anmol recently joined in this month, and she's working here at Goddard with Avi and I. Dare Bartelt is also have started working here with us. She's also another post back. She worked with Megan Mansfield at University of Arizona, and Megan, I think, is moving to University of Maryland soon. Dare is working with Kevin Stevenson and Sarah Peacock and I on prioritizing the targets for James Webb 500-hour DDT program. I'm sure you probably heard about this. And she's also running the Phoenix atmospheric core with Sarah Peacock to compute the spectra of exoplanet host stars. Dare is here. I think Anmol is also here. So if you have any questions about their projects, please ask them. And Tejinder is going to join us in January. Tejinder is going to work on the survivability of lichens and cyanobacteria under the UV irradiation of Mdwarf stars. How life can sustain. He has some interesting experiments on Martian conditions. He has a paper in prep, or maybe he has submitted it. So hopefully he'll get back. Maybe once he's back, maybe we can ask him to give a talk. I'm going to end with this one. This is a project that Rafi, a scientist here working with Thomas Fosh and I, they wanted to apply artificial intelligence for anomaly detection and reduce and try to reduce the noise in the transit data sets and identify potential spectral signatures. And I could go a little bit detail on this, but I think we're almost at the end of the time. Those are the projects right now I have. I think I'll end here. Thank you.
Thank you, Ravi. Got time for a couple quick questions, if there are any. Ravi, anybody have any questions?
I saw a chat thing.
Thanks for that great overview, Ravi. It's really nice to see all the different things your group is doing. I'm really amazed by how much you guys are doing down there. It's pretty good.
Yeah, it's all because of team. They are very excited.
Okay, good. Okay, then, if there's no questions, I think we'll take a break. 15 minutes. And then we have two invited speakers, and they're both here, trapped in this room. So we're going to hear from Roman Rafikov from Cambridge, and we're going to hear from Jackie from down at the Museum of Natural History. So see you all soon.
Right. See you all.
Thank you. Okay, so Roman's going to talk to us about current ideas on planet formation. So take it away, Roman.
Great, thank you very much. So first of all, even though today I came from Princeton, I'm actually based in University of Cambridge, even further out across the pond. And I just wanted to kind of quickly, well, maybe advertise what's happening in Cambridge along the lines of what, of what you guys are doing here. So, I mean, as you can see, first of all, I'm based at the Department of Applied Mathematics and Theoretical Physics, which covers a lot of different areas, you know, astrophysical fluid dynamics, geophysical fluid dynamics, and so on. As you can see, we are not writing too much on Twitter, you know, we are very busy people, you know, but we do have some connections to what you guys are doing. So, for example, we have a geophysics group which does work on science of atmosphere, cryosphere, ocean, and solid Earth. So in addition to that, Cambridge is a part of a big initiative, Leverhulme Center for Life in the Universe, which was a 10 million pound grant which Didier Queloz, Nobel Prize laureate, got several years ago, and established this big initiative that covers issues of you know, geology, actually philosophy, chemistry, and so on, everything related to life in the universe. So just wanted you to be aware of this thing that they're happening in Cambridge, and for some of you, maybe it might be interesting to build these connections with the place. So let's see. Okay, good. So now that's gonna be my talk. So I'm gonna very quickly talk about observations of planets. Mike asked me to give me, you know, some overview of planet formation, and I also threw in some stuff about planetary systems around white dwarfs, about dead stars. That sounds very interesting to me as a scientist as well. So speaking about observations, of course, we're all familiar with our own solar system, you know, has a range of planets, terrestrial planets, doesn't have the super Earths that we are finding around other stars, but, you know, terrestrial planets are present. We have some giant planets, which are typically divided into two classes, gas giants and ice giants. But what's important for us from the point of view of planet formation is that these giant planets, all of them, we believe, should contain cores in their centers. And the cores with masses could be, you know, 10 Earth masses, could be 20 Earth masses. Now, there is some debate that in planets like Jupiter, these cores might have, you know, kind of fuzzy edges and so on. But still, there is a concentration of refractory material with, you know, this kind of masses of about 10 Earth masses sitting in these planets. Now, going further out, looking at the exoplanets, so this is a, you know, kind of a recent snapshot of what we have in terms of planetary masses versus the period from the central star or the distance, looking at different detection methods. And quite impressively, you know, we have such a range of various methods of detection of planets, starting from the pulsar timing, by which the first planets were discovered, and then, you know, radial velocities, these green points, then transiting planets. By the way, this is just the mass measurements, so not all of the transiting planets have mass measurements. My guess is that, you know, this is all ordered just by the discovery method, not the observation method, and so on. And you can see that, you know, of course, our own solar system is slightly on the edge of this detection, that we, you know, can only see things like Jupiter and Saturn at the present moment, but hopefully situation will improve. Then if we do look at the radii of planets, at the actual sizes of planets, this is how things start looking like. And of course, in this case, we mainly have planetary transits that give us information about these planetary sizes. We also have some information coming from direct imaging, because in direct imaging, well, if you measure temperature, you know, the distance to the planet that you detected directly around the orbiting in wide orbit, you can see the periods are very long. around other stars, then you pretty much can get an idea of the size of the planet. And this is what we are having over here. Of course, in this case, you can only work with gas giant planets, with very massive planets. Whereas closer in, where we are sensitive to transits, TASS and Kepler have provided a lot of information about planetary properties. What you should probably notice in this plot is this separation into, this big cloud of dots, rarefaction in number of planets over here, and then again the cloud over at this region, which in itself gets split. Actually, there is a valley over here, which we think is due to arises due to the irradiation, or at least there's some way of loss of the atmosphere of these planets. But this valley is what I think will be sort of important for our understanding of planet formation later on. Then there is, talking about orbital dynamics. There is a complexity of orbital architectures in here, a lot of eccentric planets, detected by different methods, clear signs of tidal circularization closer to the stars, but still, a lot of dynamically rich systems, and many multi-planet systems in which we still, we do observe both circular and highly eccentric orbits. Now, this is just, mature planets as we see them. In recent years, we also got some possibility of finding planets by in their infancy, effectively, via the signs, via the imprints or signposts that they imprint on their parent protoplanetary disks. So we believe that planets form in protoplanetary disks, which are disk-like kind of concentrations of gas, which are in Keplerian, mainly Keplerian rotation around the parent stars. Disks can represent from 10 to the minus 3 to 0.1 of the mass of the central star, of course, depending on the evolutionary stage. The sizes range from hundreds to thousands of AU, and about 1% of mass in these disks is comprised of dust. So dust particles are the material for building rocky terrestrial planets, the cores of gas giants, and so on and so forth. Very importantly, we know that these disks should last from demographic studies in various young stellar associations. We know that these disks should last for several million years. Typically, we believe no longer than 10 million years. And this is very important because it sets the stage for planet formation. It sets the time window within which the planet formation should be kind of done in these systems. And of course, conditions in these disks are, could be quite different from the usual accretion disks to which we are used to in, let's say, high energy astrophysics. These disks are cold, their temperatures at like tens to hundreds of Kelvin in the innermost parts, which does mean that their evolution, sometimes it's difficult to understand how they evolve. What is driving accretion from them, even though we know that there is some accretion going on through these disks because we see the high energy emission coming from accretion hitting the central star and so on. So this all, provides gives rise to a lot of interesting physics, but of course it complicates understanding as well. So in recent, one thing is, this image which I show, it's a pretty old image of disks which were imaged directly. So this is they're imaged via the scattered light. It's a light of the central star which reflects off the surfaces of these disks. And you need big ground-based telescope for that, observing in the near infrared wavelengths. Typically, you can see that there is a richness of structures that you observe in these systems. For example, spiral arms of different kinds, non-axisymmetric features, and so on and so forth. This has gotten enhanced even more when we started looking at these disks using ALMA. ALMA has been amazing. I mean, it has been absolutely great instrument that has been an eye opener for us in terms of understanding properties of protoplanetary disks and how planets might affect these disks. We can see this is just a thermal emission of big dust particles with sizes of millimeters to centimeters. You can see a lot of different structures on large scales. The typical sizes here are like tens to hundreds of astronomical units. And what you see is a richness of various substructures. You can see, spirals over here. You can see spirals over there. There are very beautiful annular structures like here, or AS209 is one of the richest systems presenting a lot of these annular structures. We also see non-axisymmetric structures, which many people interpret as vortex-like formations in these disks. And so it has been a whole, basically, revolution that, whole discovery of this richness that we have found using just a pure dust emission from these disks. We can also use not only, why do we think this could be due to planets? Well, for example, how can you get such a richness of multiple rings and gaps in this system? So it turns out that even if and this is based on kind of simulation. This is simulations done by my former student Rubin Dong, who just took a relatively low mass planet, 10 Earth mass planet, stuck it into the disk, just a single planet, and found that actually in this case, what you see in the dust emission, this is the image on the right, is a collection of these concentric disks, rings, gaps, and so on and so forth. So what happens is that dust is actually very, very sensitive to whatever even small perturbations you can impose on a gas structure. So for example, here you can see the gas profile induced by this small planet. It kind of carves some sort of a very shallow main gap around its orbit. Then due to a certain intricacies of density wave propagation in a disk, it carves some additional gaps. And these gaps are actually perfect sites for trapping gaps and actually bumps in the surface density, are perfect sites for trapping dust. So dust concentration can reach, orders of magnitude dislocations, which gives rise to these features. So in principle, planets could be indeed a very natural way to explain these various structures. And the same goes for the spiral waves that we see in this disk, same goes for the vortex-like features, and so on and so forth. Recently, we started, doing even more amazing things with ALMA. So, for example, not just looking at the thermal dust emission and all these asymmetries, but also looking at just the data, the line resolved data. So, for example, you can take a CO line, which is CO is very abundant in these disks, and try to interpret what you see in terms of the disk-planet interaction. For example, this is a real observation of a disk, and this kind of smooth feature. This is just, taking an emission coming in a very narrow channel, and then the Keplerian motion of the gas in a disk dictates that you should stay close to this, to this kind of butterfly-like pattern. It's like a butterfly wing, which has a very well predictable shape. But sometimes in many disks, actually, you see these kind of features. You see the velocity kinks, as they are called. And one can easily show, again, using simulations, that the same kink can be very easily reproduced if there is a nearby planet. Because this nearby planet drives spiral density waves in the protoplanetary disk. Density wave is a perturbation of the gas velocity, and that shifts. If you're working in a single frequency band, that means that single kind of velocity, radial velocity towards us, and that produces perturbation in the spatial pattern, which is another way of detecting planets. So we are hunting the planets from all the directions, from all the ages, and we are finding, the current count stands into thousands. So now the next natural question is, what do we know about their formation? How do they come into being? All right, so planet formation is a complicated and multifaceted process. It's first of all, you have to climb a very tall ladder. You have to go from micron, submicron sized dust particles, which is what you inherit from the collapse of this protoplanetary cloud into the protoplanetary disk. And you need to go all the way up to the cores of giant gas giants and gas giants themselves. This is also not just, you're not only climbing the ladder, you're also chasing something. And what you're chasing is 10 million years within which the gas should dissipate from your protoplanetary disk. Because if your planet formation, if the formation of this cores is not done, then you're not going to form giant planets, which we observe in many systems. Terrestrial planets probably are fine, but giant planets do require a rather fast means of formation. And this has always been a very complicated game that we have to play, how to understand this, how you can fit the planet formation in such a short amount of time. So there are different natural stages. One of them is going from, let's say, dust to planetesimals to these kind of kilometer-sized objects. The easiest idea that people had for a long time is that you just grow by pairwise collisions. You have these small, particles or fractal aggregates as they grow. They stick. They merge. They build bigger and bigger bodies. Mass is kind of conserved, and so you keep sticking particles unless they become very, very large. There is a lot of complications in this game, and actually a lot of unknowns. One of the unknowns is the probability of particle sticking. This probability comes into actually the way in which we are following this process, this growth and merger process. Typically, the mathematical framework can be encompassed by this Smoluchowski equation, which tells us how particles get moved from one mass beam to another as they stick. So this would be like a source term. Two mass beams are getting particles into your mass beam of interest, and this is a loss term, how collisions knock out particles from your mass beam. But what's key here is this thing. This is a kernel, or so-called coagulation kernel, or which is basically determined by the cross-section for collisions and for sticking, the sticking of these particles. And this sticking actually depends on a lot of things, on like the shapes of particles, their porosity, velocity distribution of particles, and so on and so forth. And understanding all these issues is, it's a very big and complicated thing. Moreover, quite early on, we have gotten some ideas that this, just sticking shouldn't continue forever. Actually, there are problems. One of the problems you can find it if you go onto the beach. You go to the beach, you take two sand particles, throw them at each other, and they're not going to stick. They're gonna, bounce off. So there is a bouncing barrier somewhere around the millimeter or centimeter-sized particles. There are other issues, so-called 1 meter problem, because particles are actually starting to move very rapidly radially when they reach roughly this size towards the central star, and so you're just going to lose them all. And because of that, so people believe that there is some barrier to growth. So unless you can grow all the way up to here, but then you're going to get stuck on this ladder, and you're not going to have a way of going up, unless you have some other idea. And these ideas have been developed in a recent, let's say, 20 years by people like Andrew Udin, Anders Johansson, very prominently, Jeremy Goodman, many other people. They have shown that if you start with a gas disk which is laden with dust, and you take into account the fact that gas and dust are moving differently, they can slip against each other, and that dust can actually back react on the gas, even though it's formally is just 1% of the mass in a system. Then in this case, you can drive certain instabilities, non-axisymmetric instabilities that would create particle clumping. So this, what's shown here is the density of particles, and you can see these bright features emerging. This is just concentrations of dust particles, which eventually start gaining more and more mass inside of them. They become self-gravitating, and they actually collapse and form asteroid-like bodies. So this, in a way, it's a way to bypass, to kind of jump around this 1 meter problem, and to produce objects with sizes of several kilometers or tens of kilometers right away by just application of this instability. So there is a lot of work right now going into understanding the conditions under which this scenario would indeed work. Then going from planetesimals to planetary cores, well, this is a bit probably a better understood process. In this case, you can consider, like zillions and zillions of these kilometer or 10 kilometer sized planetesimals. Their orbits overlap, they can collide with each other freely. So it's like a gas of planetesimals. So it's a gravitating system. When velocities of these, relative velocities of these objects are not very high, gravitational focusing becomes very strong. That is a perturbation of one massive body by the other that can increase the cross-section for growth. But this again, complicates, there is a complication in this case, because when velocity dispersion starts, when when things start depending on the gravitational focusing, then the velocity dispersion of these objects becomes also very important. And so you need to understand dynamical evolution of this planetesimal population. And this is where, there are some interesting details on which many people have worked over the years. Nevertheless, you do find that, growth in this case can be relatively easily modeled. Things do grow, you produce planetary cores, and that's kind of all nice. So following that, you enter the last stage. How do you produce a gas giant? How do you produce the most massive planets that we see in the universe? And in this case, there have historically been mainly two ideas to explain the formation of giant planets. One of them is an idea of core accretion. Core accretion is pretty much a bottom-up scenario. So in this case, you first build these planetary cores by this coagulation process, starting from planetesimals to planetary embryos to finally cores. And then once these cores are immersed in the nebular gas, so they actually attract gravitationally an atmosphere around them. At some point, as the core mass grows, the atmosphere increases and finally it becomes self-gravitating. And what happens is that you have a so-called runaway accretion of gas. This is roughly represented on this plot, which kind of is a model of Jupiter formation at 5.2 astronomical units. Each curve, each color represents certain surface density of material at this particular location. So for example, if I look at the blue collection of curves, then the solid curve is a growth of the solid object of the core. Then this dashed line is the amount of gas. And you can see that the amount of gas increases dramatically as the core mass approaches something like 15 Earth masses. So beyond that point, you have this runaway gas accretion, and very, very rapidly from 10 to 20 Earth masses, you suddenly gain in a short amount of time, very large amount of mass. So this would very naturally explain this separation in a radius versus distance in that plot, from Kepler and TESS, which I showed initially, because it shows that, planets are not going to get stuck in this regime with intermediate mass for a long time. They're going to accrete so much gas that they're going to become giants very, very rapidly. This scenario is beautiful. It explains many things. However, it does take time because you need some time to build this course, and this is this can be quite a slow process. So alternatively, this is an idea that has been developed for a long time, an idea for which Al Cameron and Alan Boss have contributed a lot. Is that these planets can be formed in very dense and massive disks, in which you can have the phenomenon of gravitational instability taking place. When a gravitational instability is happening in a disk, you create these violent, spiral arms, and sometimes these spiral arms can actually fragment into pieces and give rise to these quite massive objects, which immediately collapse into giant planets. So this would be a top-down approach in which you immediately start from large scales and get very massive planets on essentially dynamical timescales, so within several thousand years, let's say. Okay. The problem is that for this scenario to work, you also need the gas also needs to have an ability to cool effectively. And I have shown like 20 years ago or so that actually this would probably allow this mechanism to operate only very far from the central star, only at separations of, let's say, 70 to 100 of astronomical units. And the general consensus in the field is that, yes, this is probably what's going on. So in a nutshell, this is all our journey through the planet formation process. And I would be happy to answer, questions, after the talk or offline. And then in the remaining 2 or 3 minutes, I wanted to quickly flesh out some interesting results about these planetary systems around white dwarfs and why they could be interesting for some of you who work on, like magma oceans, internal dynamics, tectonics of planets, and so on. So there is this particular class of white dwarfs, and white dwarfs, as we know, are dead stars. We heard about them already today, what happens when they die, what happens to the planets. Some of these white dwarfs actually have very strong metal pollution in their atmospheres. So they show metal lines in their spectra. And this is quite unexpected because you do expect to see only hydrogen or helium in their atmospheres. The gravitational acceleration on the surfaces of white dwarfs is so strong that any metal that you drop in there should very quickly sink out of your side. So you shouldn't be seeing any metals unless they are being constantly accreted, unless there is something that supplies these metals. It can be shown that accretion from the interstellar medium is insufficient to supply the amount of metals that we see in these systems. And so what people think is that actually there is some circumstellar material that exists around these white dwarfs that keeps getting accreted onto the white dwarfs. And this circumstellar material comes basically from the planetary systems that existed around the progenitors of these white dwarfs. In confirmation of this idea, we also found infrared excesses around many, many white dwarfs. Not as many as are metal polluted, because metal pollution is a very common feature. 30 to 50% of white dwarfs are metal rich. But these disks are found around, maybe several percent of these white dwarfs. Nevertheless, we do know that these are disks of solid debris, which is located very close to the white dwarf. So it's like within 1 solar radius from the white dwarf. And we see the infrared emission coming from these disks. Like, for example, here, this is a white dwarf, and this is this big whooping infrared emission feature that's due to this reprocessed light due to the white dwarf. This, by the way, would complicate detection of any planets around white dwarfs or their interpretation, because this is a very whooping signal compared to what you can expect from like the Earth's own light from any planet around this white dwarf. Why this is interesting? Well, it's interesting because these systems then provide us with the only way to kind of figure out the bulk compositions of the extrasolar bodies. So any other method, for example, transmission spectroscopy or anything, own emission of the giant planets and so on, is telling us what we see just in the atmospheres of these planets, the composition of these things. Last slide. And in white dwarf atmospheres, we sometimes see up to 10 to 15 to 17 different elements, and we can build the ladder of these element ratios. And you can see, for example, in this white dwarf, this is, I think, again, GD, 362, the elemental ratios of elemental abundances are essentially the same as what we see in the solar system around, Moon, Mars, or Earth. And this is quite encouraging. So basically, what I'm saying is that, the white dwarfs are giving us a whole natural laboratory. You just take a whole planet, you grind it down, to pieces, and then the spectroscopy is allowing you to, instead of going to the lab, you are just seeing it in the light from the star. Like in our own solar system, we can go in Arizona, we can, knock out some rocks and so on, or we can, study meteorites that fall on Earth, but we don't have a means of doing that, in an extrasolar system. So these white dwarfs are actually doing this for us. And this is, for example, a sample of different white dwarfs with different amounts of magnesium, silicon, iron, oxygen, and so on found in them. So I do hope that some of you who are interested in bulk compositions of planets will take a note of these amazing systems and will actually kind of, follow up this field, expand in there, try to model these things maybe, or use them at least to constrain your models. So thank you very much.
Time for a couple quick questions. Yeah, Kevin. This is a naive question. Since planetary formation involves these instabilities, is there any way to detect dark matter this way?
What do you mean dark matter? Cosmological dark matter?
Yeah. Will this affect the instabilities in planetary formation?
No, I don't think so. We think effects of dark matter,
very small,
on solar scales are very
small. But
there is a lot of violence going on when you just have this initial inflow of stuff onto the protoplanetary disk. So I'm sure this will swamp out any of these, tiny weak effects.
Donnie?
Yeah, maybe I missed it, but so is it the case that the metals that you're seeing in the stars, we're assuming that's from the planets? That's accreting from the planets?
It's not assuming. No. This is just a measurement of the strengths of these spectral lines. You can see that there are lines of silicon, magnesium, calcium, and so on.
But this is from the star.
This is from the star. This is what finally ended up in the photosphere of the star. Then you use models, but there should be no metals there from the start. They should have all sunk. Then you use models which tell you what is the thickness of the convective layer on the surface of the white dwarf and what is the sinking time of these metals, which is, subject to some theoretical uncertainties, but is still, reasonably good, reasonably calculable thing. Right. And then you reconstruct the amounts of mass in different metals in this white dwarf. So this is, for example, mass in calcium in the atmosphere of different white dwarfs with different effective temperatures. Okay, and the amount of mass is consistent with size of Minerva or Vesta or Ceres in many systems. The relative if you're interested in relative abundances in these things, then yeah, this is just looking at a single white dwarf and taking these ratios of these masses in different elements. So it really measures directly the composition of whatever has fallen into. Eventually, it's not like it fallen into the atmosphere. It must have been tidally destroyed, ground down, and accreted through these debris disks. But it's still, relative abundances are reflecting the bulk composition. I'm talking about bulk, like what is in the center of your object, the crust, and so on and so forth.
Awesome. Thank you. Okay. We have to move on, but Ramon's going to join us for dinner, so you can interrogate him more. I have some interrogation questions too. I think Jill Knapp was one of the first to measure these metals in these white dwarfs when we were at Princeton in the 90s.
Okay.
Okay, Jackie, your turn.
Okay. Can folks hear me on the Zoom? Because I'm kind of far from the owl.
Can you all hear Jackie on the Zoom? No, maybe you should come over here,
I'll
Jackie.
get closer
I
to
think
them.
that those things, I think are also might have.
What?
If they're plugged in, I don't know if it's plugged in or not. That might be the old system. I'm not sure.
Well,
Yeah.
maybe somebody could say in the chat if they could.
Can anybody hear Jackie online?
Can you hear me?
Yeah.
Yeah.
Okay, you can hear me.
Good.
Okay,
Thank you.
great.
Go for it.
All right, and Mike, just tell me, what should be my stop time?
In exactly 30 minutes.
30, so
Well, 25 would be great, so we have some time for
25,
questions.
yeah,
Be good.
okay.
But we can also interrogate you at dinner. so-
Yes, you can. I like to be respectful of time and make sure I stop right when I'm supposed to.
It's
But
actually-
you'll give
I'll give
me
you a 5.
the 5 minutes. All right. So I'm a little bit of a different speaker for you guys.
That's why we invited you.
Okay, so everybody should get excited right now. It's slightly different, but I gave a version of this talk at the Cobley Prize was given recently for exoplanet atmospheres. One was given to Sarah Seeger and one was given to Dave Charbonneau. And I was one of the invited speakers there to give a talk on atmospheres. And it's a funny thing to get invited to such a prestigious thing when it was to bring in people that are at the forefront of exoplanet atmospheres when I study brown dwarfs. These objects are in between stars and planets. But let me just start by arguing first why you guys should care and be super excited about what I'm going to show you. So in 2000 and whatever year it was, 20, the Nobel Prize, maybe it was 2019, now I don't remember. The Nobel Prize was given for the discovery and characterization of exoplanets, right? We all remember this? Yes?
Yes.
And this was the paper that was kind of the spearhead of this field of exoplanet research, a Jupiter mass companion to a solar type star. As a reminder, it was the star 51 Pegasi, and the planet found around it was Jupiter mass, but it was super tight on the star. So tight that at that time, it's a Nature paper from 1995, Michel Mayor and Didier Queloz were the authors. But remember this, in the abstract, you might not remember this, they didn't know what they'd found. Could they have found a planet, quote unquote planet? Or, this is in the abstract, people. Abstract, right there. This object might be a gas giant planet that's migrated to the location, or it might be a brown dwarf that has been radiative stripped and is sitting there at this close-in distance. At the time, either one was exciting and could have won us the Nobel Prize as well from the brown dwarf science side of it. But nobody had found a brown dwarf yet. So in later that year, November 30th, 1995, was the revelation of a cold brown dwarf. It was a paper led by Takanori Nakajima, as well as Rebecca Oppenheimer, who I work next to at the American Museum of Natural History, and several others from Caltech and other places. The first revelation of an atmosphere for a cold, compact object. This one actually had a host star. It was this object called Gliese 229b, and it was orbiting an M-type star. Recent discoveries, this is about to come out in another Nature paper, that brown dwarf is actually two brown dwarfs. It's actually a binary. It's a new discovery.
Binary orbiting an Mdwarf.
Yeah, a binary brown dwarf orbiting an Mdwarf, where there's also a Neptune-sized planet that's also in there. You're gonna solve that for me at dinner, okay?
Yes, it's your paper.
Solve that one, please. But point being that we, brown dwarfs are way ahead of the atmosphere game, because we mostly don't have to have a host star to deal with. And even when we do, we are far away enough from the star that you can just drop the object onto a slit and directly observe the object. So I'm going to show you guys a library of spectra that I've been accumulating from the James Webb Space Telescope and argue why this is such an important data set for us all to focus on, even if what you want to find is the biosignature around an a planet that's getting irradiated by its M-dwarf host star. All right, just a little bit more background on this. So brown dwarfs are objects in between stars and planets. Now, the other thing that I usually start with is say the word planet, people, is idiotic. I'll just let that sit with you all for a second. It doesn't define the objects well at all. I just listened to this amazing planet formation talk, but you didn't mention the brown dwarfs in there, but they sit in these same diagrams. And so what is a planet? I dare all of you to go into a DPS meeting. Yeah, Pluto, fine. Yeah, this is what I'm gonna say. Walk into a DPS meeting and just shout out, Pluto isn't a planet, and see if an all-out brawl doesn't happen. People get very sensitive about what you call planets and what you not. Now, Pluto's not the only object that draws a problem for the word planet. The high mass end also has a problem. You can find isolated Jupiter mass objects. Are they ejected? Did they form in situ? Somebody's gonna solve this. Look at you, sir. So either way, I prefer not to use the word planet as much as I can, and instead I use the word world. So that seems to get a lot less emotional for most people, and I think it's far more encompassing of what we're actually studying.
I think you'd be emotional about the word world also.
I'm just an emotional person. So real quick on brown dwarfs, these objects in between stars and planets. So of course we think that the differentiating factor between them and stars is that they're such a low mass that they cannot get hydrogen burning in their cores. So that's not a bad definition, except for the fact that we cannot tell whether you're burning hydrogen or not. There's no detection of whether you're in a hydrogen burning phase or not. We don't have anything that I can measure off. So there's actually a confused area where I don't know if I've got a star or I've got a brown dwarf. So they're super mixed. Trappist, yes. Most people in here will like Trappist. Favorites amongst them. I studied Trappist in grad school because we didn't know what kind of object it was. It's at the hairy edge of being called a star. It's literally barely a star. It's like 78 Jupiter masses. I had a student that worked on this object. It's so barely a star. It's almost a brown dwarf. Great. Why? What would we call that system of 7 rocky worlds around it if we didn't call that host star a star? I'll just let you guys ponder that. The bottom end, that we have a terrible definition for where you're going to stop the brown dwarfs and start the planets. The coldest compact objects that we have are called Y-type objects. I'll just zoom in for you to just show you our brown dwarf spectral types. M-types, Trappist, great. Also, everybody wants to find their world around rocky. I've got lots of brown dwarf M-dwarfs though. I got lots of them. 35 Jupiter mass M-type objects. They also have little worlds that are orbiting around them. Nobody's coming to me and looking for their biosignatures, but they might be there. They might be there.
Any within 20 parsecs?
Yes.
Okay.
Yes.
No.
Bobby, why did I?
If you're on this call, don't forget.
I mean, they're not necessarily, they're in nearby. They're not within 25
Okay,
parsecs.
now she changed her story.
I did change it. I just wanted to give you, yeah. All right. But then the Y types are really where I'm going to focus the rest of this energy for the rest of this talk, because those are so cold. They've been so hard to find, but my team has done crazy amazing things at finding Y-type objects. There's about 40 of them that are known, the coldest of which is about 250 degrees Kelvin. 250 degrees Kelvin. That is roughly 125 or so degrees Kelvin warmer than Jupiter. The Y-type that is the fourth closest system to the sun. Number 4, kids. Number 1, Alpha Centauri system, right? Number 2, Barnard star. Number 3rd closest system to the sun is also a brown dwarf system. I can give you a whole other talk on that one. That one's crazy. And then this one, the 4th closest, it was only discovered a decade ago because they're so hard to find. But then when you get them, you're basically studying an extrasolar atmosphere, an extrasolar cold world. And I have a bunch of them that I'm going to show you a library of that we have been winning James Webb Space Telescope time to characterize the atmospheres. But before I do, I just want to tell you why it's hard. So you might naively say, all right, you figure out, you get a spectrum and you can just organize them, right? You can just organize them. You can just figure out what's happening in their atmosphere. Absolutely not. 100% not going to happen for you because of all these secondary parameters that are driving things. Metallicity, gravity, their age, non-equilibrium chemistry. The bane of my existence is non-equilibrium chemistry right now. Binarity. You don't know if you're looking at 1 or 2. It's going to come up, people. You want to find your little rocky Mdwarf planets. You don't know if you're just studying 1 rocky planet or 2. Maybe there's 3 in there. What's that going to do to your spectrum when you're trying to figure out your data? Your viewing angle. Have you even thought about this? Are you looking at a polon? Are you looking at an equatoron? Better figure that out. It's going to change your clouds. And the clouds are going to make your life HE double hockey stick. Total hell. Then aurora, I'll give you some of that because that's something that we didn't see coming, but we got. And then vertical mixing. Some of these, if this were a Venn diagram, you'd see that they're all meshed up with each other, but it's chaos. All right, now I'm going to show you. So we're going to get all spectra of all of these. So I'm going to be respectful of time, and now I'm giving you too much passion. All right, periodic table. What do we detect in the brown dwarfs? Because we have so many of them, we have a library of thousands, and these are the kinds of elements that we can directly detect and give you abundances for. Hydrogen, lithium, sodium, potassium, rubidium, cesium, titanium, lots of alkalis. We see a lot of hydrides and a lot of oxides, but I'm going to focus on the coldest ones. And for that, I'm going to focus on these elements: carbon, nitrogen, oxygen, phosphorus. I'll tell you why in a second, because they form these molecules which dominate the cold objects: hydrogen sulfide, ammonia, methane, phosphine, carbon dioxide, carbon monoxide, and water. This is an example of a model spectrum of what you might expect for a 450 degree Kelvin object. I'm going to show you now what a James Webb Space Telescope data set looks like for this kind of object. Are you ready? Are you ready? This is real data I'm about to show you. Real stinking data, exoplanet people. Boo. This is very slow transitions.
Yes.
Real stinking data, people. Damn. And that every wiggle you see is real with a capital R. Super real. This is crazy. Yeah, 450 degrees Kelvin.
This is Miri?
That's MIRI and NIRSPEC in their highest resolution.
Yeah, I was saying this is really high.
Yeah, this is the high resolution data. This is the only one I can show you that has this level. This was actually a GTO target, but I'm going to focus in on this area of NIRSPEC because it's the peak of the spectral energy distribution, because that's where my library came in. I had time in JWST cycle 1 to develop the library of cold objects.
Is this letter around 10 microns? Is it CO?
There is a CO2 feature out in the mid-infrared, but the CO and the CO2 is dominating this area between 3 and 5 microns. You're about to see it. If you're ready, I'm going to show you some CO and CO2. All right, this is just to give you an idea of what molecules are there. This is some cross sections that are overlaid on top of a zoom in on the G395H NIRSPEC data for that same object 1828. Now I'm going to show you a movie. I'm going to show you a movie of a bunch of them. This is highlighting for you what you're looking at. So that's the carbon dioxide feature. Every wiggle is real. Every wiggle is real. It's all molecular absorption, people. This is not a joke. This is real data. This is what you want. You don't want just your transmission spectra that barely show you things. This is it. I will
We need
say.
this to understand the transmission spectrum. What
my
are you talking about? We all know
Dude,
that. We
this.
know we need it.
One thing I will say, if you were to go upwards from Jupiter, you would have just thought we should have been swimming in phosphine. We should have been swimming in it, and we don't see it at all. No stinking phosphine. That is a mystery to us. There's also hydrogen sulfide in here, but it's subtle, and so I can't really give you everything else I'm going to show you in the next movie is going to pop out to your eye like crazy. All right. Here's a movie. I'm going to show you objects from 800 degrees Kelvin all the way down to 250 degrees Kelvin. We worked really hard to get this library, and each one of these features is pointed out to you. I don't think my pointer, oh, it does work. Okay. So follow this methane feature. You see this? Methane just, boom, sucks the life out of the spectrum here. This is another methane feature. Look at this CO and CO2. That CO2 is freaking gorgeous. And then this is like ringing like a bell. See that CO, it comes up and then up again. Wonderful. And then all these lines in here are water. Now I'm going to play this for you that should show you what temperature does to the library. Get ready. All right. You're just going to keep watching it. Oh, I forgot this is Zoom. It might be a little bit wonky. Okay. But you can see.
This meeting is being recorded.
Oh, that's okay. Now you're recording me.
No, that's weird.
All right, so watch these spectra as they change in temperature. You'll notice that the last one, I call 285 degrees Kelvin because we're all kind of debating the final temperature of that object. I think it's probably more like 250, but a recent paper called it 285. Look at the methane band. Watch that methane band. That methane band, gorgeous. It sinks. It gets deeper and deeper and deeper. And something popped. Something popped in that methane on an object. Watch the CO and the CO2. What I call this is utter chaos. That CO and that CO2 is following no sequence whatsoever. It is in complete and total non-equilibrium. It is not following what temperature would tell you. Notice 397, at 377, all of a sudden it drops to this crazy amount of CO2 absorption. Why? Excellent question. Vertical mixing, we think that one has a slightly higher metallicity, and the CO and the CO2 are crazy sensitive to metallicity. All right, a couple more things before I stop. This is part of the library. I know, Mike, because
No, it's okay. You're
gonna
fine.
go
You're
over
fine. I was just checking.
This is just a zoom out to show you the whole library in context, all of them together. I showed you in the movie. I could stare at that movie forever, but I'm going to zoom in on the one that.
What is this? What's on the left and what's on the right?
Oh, okay.
I
So
can't read things.
the left hand is just showing you normalized flux. The bottom, this is just a zoom in on all that data I was just showing you. And now I'm showing you lined up with temperature. The warmest one is at the top. The coldest one is at the bottom. So you can look for those same features that
What's the wavelength on the right
It's 3 to 5 microns.
from the one on the left?
It starts over here at 3 microns. Oh, it's not letting me do it. My pointer isn't working.
Oh.
The left-hand side is 3 microns. The right-hand side is 5 microns. All right. The most important thing is I want you to look at that methane. The methane, remember, is in the first set of panels. So I'll zoom in on it. So we'll just have a look at that. And this is where we noticed something that was like, huh, what just happened? You see that gorgeous methane band. So at 3.3 microns, there's this second big absorption. It's like, you look at the cross section, you just see it. It's just wiping it. But let me highlight it for you. There, you see that? Boom, boom, boom. But then we had one that stinking had emission. This object is 450 degrees Kelvin. It should not be emitting.
Yeah,
that
why?
means the methane was glowing. Yeah, why does it happen? Why does it happen? Why did it happen? That's what we asked. So I'll just zoom in on that object again. This is from some press we got on this object. It had a clone, another object that looked just like it. You can see they're sitting on top of each other. They had basically the same amount of water and ammonia. They had basically the same amount of carbon monoxide, of CO. They basically had the blue versus the white are two very, very different objects. They are not the same object. They are different distances. They formed in a different way, or they formed from a different cloud.
Very similar temperature.
Very similar temperatures, but the one has the methane and the other does not.
Is it metallicity related?
That is let's zoom in just so you can see it there. No, but I'll show you what we did. We had to model it. We're like, what is that? First of all, we couldn't figure out that it was emission. The bottom of this axis is your temperature, and the y-axis is going to be your pressure. So if you were going to stand above the atmosphere and go to take a dip in the pool you'd see the temperature should change like that. And in the object that didn't have that methane emission, this is what you would expect the temperature pressure profile to do. But in the other object that showed the methane emission, it did this. It required a 300 degree Kelvin temperature inversion centered at 1 to 10 millibars. Why does that happen? That is what we asked ourselves. Why does that happen? We turned to the solar system and we said, okay, does this happen in the solar system? And it does in Jupiter.
And it wouldn't affect any other elements, only the methane?
Exactly, yes. And the reason is because the methane is higher up in the atmosphere. So it's literally what's happening. Oh, we have a prediction for cycle 4. We think that the ammonia will also light up. If the JWST time allocation committee will give us time to get that MIRI data, then you'll see a second emission, which nobody has even shown me in Jupiter yet.
Data covers the ammonia feature?
MIRI covers ammonia, nitrogen chemistry. Think of it as MIRI does nitrogen chemistry and NIRSPEC does carbon chemistry. But Jupiter does have an aurora that's going off. Now, Jupiter's aurora, what is it from? It has the largest contribution from the solar wind. The solar wind comes at it just like it does on Earth and lights it up, but it has a second major contributor. And that's Io, a rocky, explosive moon, active moon that's orbiting Jupiter. Our object is about 30 Jupiter masses. We don't know. I'm not saying it has a moon, but I'm kind of saying it has a moon. You know what I'm saying?
That's what you said downtown.
Yeah, because there's no way for me to figure out how to insert 300 degrees Kelvin of energy from the object itself. It's not self-generating its own energy, even if it's not spitting out a plasma and then reabsorbing it.
Then it would be periodic, wouldn't it?
Well, no one let us monitor it yet. So yeah, we actually have something out that's a radio detection.
Oh, radio detect. Okay.
Yeah,
You have time resolution and radio for this object?
we don't have time resolution. What
Even
we're
the technical
just trying to measure is the magnetic field around this object. So we got VLA gave us time to look at it. We just have not yet reduced the data. But
It's just one picture.
one picture for now. Then attack will give us time later. Yeah, I'm gonna just skip this because I want to show you one more thing. But if you want to talk to me about other things on that object, great. Back on this library, we have been trying to solve this library. It is only 14 objects. That's what we have to offer the community. You want to find a biosignature? Wonderful. First, you have to be able to figure out your atmosphere, though. You have to be able to break out the binaries. I have 2 binaries here. You have to break out what a low gravity object might look like. You have to figure out what strong disequilibrium chemistry does in vertical mixing and why you have molecules sometimes and don't. We did detect phosphine in one object and one object only, and it was the coldest object. But I don't think we understand phosphine chemistry at all in these objects. Just so everybody can hear that from me. We don't understand phosphine. Clara's on board.
She would be.
She
a
is.
phosphine person.
Yeah, but it's not her fault. The fault is in the objects.
Yeah.
It's not necessarily like.
Well, she doesn't understand this chemistry either.
Nobody does. It's something to do with how phosphine exists in these temperatures and pressures. Probably also it's atmospheric because there's all this vertical mixing that's churning.
In Jupiter too.
Yeah. So you see a lot of phosphine in Jupiter.
Yeah.
So much that we thought for sure in these warmer objects we would be detecting it.
No, I think these only see the colder objects.
But the coldest ones that we have,
You don't see it.
we don't see it at all. I know. Agreed.
But
All
it's
right.
in chemistry.
Yeah. I'm gonna show you one other odd object, and I'm just gonna show it to you guys, but don't talk about it because it's super
It's
secret.
on video.
Who's gonna watch the video? Okay. I want to show it to you because I want you to be excited. This is our cold library. Look at these objects and appreciate them. I told you I think this is chaos. This is a chaos library in many ways. The carbon chemistry doesn't follow a sequence. The methane is also chaotic. It's not following a clear temperature sequence. The water lines even, they vary. I can't go into all of that for you, but they do. I'm going to show you an object now that we just got the JWST spectrum, and I'm going to stick it in here, and it's roughly where it should exist in temperature. Okay? And you're going to see why it's so stinking weird. Ready? This will be slow. Yeah, what? I thought this was an alien megastructure when I saw it. Somebody's working with Avi Loeb. Do not share this with anybody.
Okay, but you have a completely different metallicity from others. Do you even know that yet? You don't know anything about this object. do you?
Listen, I
Yeah.
do know. I do know a lot. I
Okay,
do know a lot. We suspected this to be a halo brown dwarf. But yeah, all we have it, this thing is at 16 parsecs. This is sitting in your backyard, sitting in your backyard. We didn't know whether this thing was gonna end up being some weird white dwarf. We thought, not sure what this is gonna end up being. It could be some stripped out neutron star, but no, it is definitely a brown dwarf. And you see there's that methane, gorgeous methane. That is the deep methane. But what you also notice, no CO, no CO2. None of it is there. And instead, look at what we have discovered. This, because I can't point it out, I have to walk to the front. Sorry, Zoom. You see this thing?
Yeah.
Brand new stinking detection of a molecule that no one has detected before in a planetary object. We think it's in Jupiter. I had to go through this whole, I didn't know what it was. It took me a while to figure out what was going on. That, any guesses? No guesses? You guys could probably guess at something. All the hydrogen is anything that's here is going to match to hydrogen. So all we really have is CH4, methane, H2O, that's where all the oxygen went, and then that thing, it's called silene, SiH4. It's getting dredged up from really deep down. Si stinking H4. Yeah. So Jupiter has it, but they haven't actually detected it in Jupiter yet.
Has it, but they haven't detected it. What do you
They
mean?
have a limit on it. There's a limit on what the silane is, but we have officially and not even minorly detected it. We've whoppingly detected it. The exoplanet community is all about this molecule, by the way, because you can get SiH4 if you're going to dissolve away a planet, you may be able to detect some SiH4.
55 cancrete.
Maybe. So, but this thing is maybe 30 Jupiter masses. It's probably as old as anything that's formed. It is literally a relic of the early part of the galaxy, and it is sitting there at 16 parsecs. Why is it there? I don't know. How many of them should exist? Probably not a lot of them, but it's there. All right.
It's in the lower end of the mass function. It could be.
Yeah, but the mass function trails off. So the thing is that the fact that we found it, it was really, really hard to find. We actually call this object the accident because we accidentally discovered it.
Luminosity is.
It's
zero.
so faint.
Come on.
It's so
You
faint.
barely found it.
You think it's a halo object from its kinetics?
Oh, yeah. It's moving at about
Oh, yeah, what's the
200
proper motion? Yeah.
Yeah. It was moving like a banshee when we found it, the proper motion. Then we measured the parallax and we found it at 16 parsecs and we were like, so it's at 2.5 arc seconds a year.
It's coming through.
And it's zipping. And then we got the radial velocity out of this data, and the radial velocity is about 130 kilometers a second. So this thing moves about 250 kilometers a second. It is zipping. Yeah. This is the chaos that happens when you lower the metallicity too. Oh, I love this object. I'm writing it up right now, so it's also nice. All right, and this is just my summary for you. You want to do atmospheres, you got to solve all this
Okay,
stuff.
Jackie, but
And
the people doing ground-based stuff for around Mdwarfs know this. They know that they have to model these planetary, the solar atmospheres or world atmosphere, whatever you want to call them, to high precision. Otherwise, you can't subtract it out from the planetary. That's known. That's already known. I mean, the people that use CryRes Plus down at ESO.
No, but I don't even mean
They
the
do-
host star. I'm talking about the planet.
No, I'm just saying, but at least when you're like looking at, you know, I hate to use the word planet, but you know, terrestrial planetary
Yeah.
atmospheres around Mdwarfs, it's well known that you've got to model that stellar atmosphere extremely precisely to take it out so you can see what the signal is. That's well known.
Yeah.
They're using these very sophisticated models to do that.
But-
And so stuff like this is extremely important, but it's known. I think
No,
everybody
no,
knows.
no. I think that part of my point is even bigger than this,
Okay.
because it is, the exoplanet community is making a lot of declarations
Yes.
of molecules detected.
Yes, yes, of course, it's all.
What was it? Dimethyl sulfide. Thank
Yes,
you.
yes, yes. Oh, we know, yes, that.
First. Oh, I know, but first, but my point would be, before you jump to a new molecule in any atmosphere, yes, model your host star and get it out of there.
Yes.
You have to realize that until you can explain to me, we've worked really hard on viewing angles.
Yeah.
Are we staring at these things? Because before I can tell you, I understand that I've got some patchy enstatite cloud
Mhm.
and one of my objects, I want to tell you how polon or equatoron I am to the object. And I want to know also what the non-equilibrium chemistry is very likely going on in that atmosphere before I'm going to jump to biosignature. Because I have heard a lot of exoplanet people being like, we will find that biosignature. Do not find that biosignature until you can figure out all these parameters in your objects. Yeah. Do you agree?
I agree.
Okay. You agree?
I think I'm gonna argue with you.
No. That was the last talk of the. All
I've
right.
never argued with you, Jack, I believe.
So I hope that gives you a little enticement on our amazingness.
Yes, thank you
that we
so
have.
much, Jackie. Beautiful.
So what is the letter of these lines? You know, the whole complex of, you know, absorption lines, or, you know, is this like, what is this?
It's 3 to 5 microns. Wait, what?
I mean, what is this, you know, in this object around this methane absorption feature?
What's all this?
All of that is methane. All of that is
This
methane.
is all methane.
Yeah,
This
yeah.
is all methane.
If I go back and then you'll see from a couple slides, I was trying to show you the cross sections of what the molecules do. Like in here. Ooh. So in these cross sections, like you end up seeing, it's so painful how slow it is. But you see how this is the cross section for methane. So whatever's down here is what you should see absorbing. So that's why I was saying there's this big molecular absorption from methane here. But all of this is also methane. All of this is these like vibrational modes of methane here. And then,
You're seeing this high res data.
yeah, this high res data, this resolution of 3000 roughly.
Yeah, I have a couple of questions. Do you have a metallicity for that thing?
Yeah, well, we've retrieved it and we think the metallicity is about minus 2.2.
Low, but not crazy low.
It's not minus 3, right? So the other thing is what we expected is that changing the metallicity even just a bit in these objects should drive them to start looking strange, because this molecular chemistry is so sensitive to the metallicity. So that other object I showed, I don't know if you remember, but I said at 377 degrees Kelvin, this one object showed this deep CO2. I think that one's slightly higher metallicity, which is why it goes off the cliff and all of a sudden gets all this CO2 absorption. Because the metallicity was changed just a small
Your
amount.
library is woefully incomplete.
Well, look, the exoplanet community just got 500 hours
yes.
of DDT time to say yes or no to rocky planets having an atmosphere. This library was about 24 hours of JWST time for us to demonstrate this level of precision on what might be in the atmospheres. I'm just saying the TAC should maybe spend a little bit more time building libraries like this one. Any of you end up on the TAC, please give us more time, because all I was able to get was 3 to 5 microns for our library. I want that whole library.
You can get some of the shorter wavelength stuff from ground-based, right? So what are you doing
These
there?
things are too faint. You can't do them from the ground.
Nothing.
It's literally,
Even with DLT and-
no, you can't. They're nothing. No flux comes from them. None. They are so faint. Yeah. Trust me,
believe you, no.
we used every possible instrument on the planet to go after these.
Okay, I thought Rebecca had this program for years looking at these brown dwarfs, but these particular ones are too faint. you're saying?
The ones that I'm talking about
Yeah.
take us into the absolute no flux coming out of, like Gliese 229b, all the early ones were warmer. This is the coldest that we have.
Integration times do you
It's so fast with JWST.
It's huge. There's
But
no
I mean,
external-
the other, so this is the flux. So you see the peak of the flux for these things comes at 4.5 microns. You can't observe 4.5 microns from the ground
No.
because
Well,
the
some
atmosphere.
objects you can, but it's different.
Yeah, these objects are way past what's possible. The atmosphere is super bright. You can do bright objects from the ground in the mid-infrared, but you can't do these objects. And then just look to the left of it. Do you see the near infrared? Those 3 teeny tiny little bumps there? That's why they have no flux coming for you. And then go to the optical and it's a joke. It's an absolute joke. They give
So
nothing.
HST, you can see.
HST is, we use it for the near infrared, but you
Oh,
can't
for the near
use,
infrared, you can't
yeah,
use this-
there's
this
no
stuff.
optical
There's
that's
There's
gonna,
nothing there.
you got nothing there.
It's just not a big enough aperture.
If somebody
You wouldn't
builds,
necessarily bumps there.
yeah, no, nothing,
wouldn't see
nothing, there's nothing, but I mean, we would love to get some optical because I would love to get a volatile to refractory ratio of these objects. We actually have a little bit of a plan to try that because you can get lithium out of some of these objects. There's no lithium possible out of any of the objects thus far that we've done, but we might be able to get it, might be.
That'd be very interesting.
I wanna do, yes,
Because
so,
these things are old, coming
Yeah.
from the halo, that puts serious constraints on lithium ones in the early.
oh, yeah, I didn't even think about that, but yeah, lithium's just a little complicated because it breaks into all those extra molecules, like you have to figure out lithium fluoride, lithium hydride. I've been working with Shannon Vischer, who's a chemist, he's amazing, and he's helping us figure out what is really chemically possible at these temperatures. But we're pushing the limit of possibility in these sources.
See that?
Okay,
Okay,
let's stop sharing.
let's thank everybody for their wonderful talks today. And we will reconvene tomorrow.